temperature, and the birth of stars in molecular clouds. Deep within the galactic arms of spiral galaxies like our own Milky Way, far from the blazing luminosity of stellar hubs, lie enormous, shadowy nurseries known as molecular clouds. These cold, dense regions are composed primarily of molecular hydrogen, dust, and trace elements, and they are among the coldest places in the observable universe. With temperatures often falling below 10 degrees above absolute zero, these regions offer a paradox. It is in the frigid silence of these dark clouds that the heat and brilliance of stars are born. To understand how temperature initiates the transformation from dust to brilliance, one must first grasp the delicate balance that defines a molecular cloud. Internally, these clouds are in a state of equilibrium, where gravitational forces pulling inward are nearly matched by thermal pressure pushing outward. However, this balance is fragile. A slight drop in temperature can tip the scales, allowing gravity to begin compressing the cloud's material. This process, known as gravitational collapse, marks the very first step in the creation of a star. But what causes this cooling? Interstellar dust plays an instrumental role. These minute particles, no larger than smoke grains, are efficient radiators of heat. They absorb starlight from distant regions and re-radiate it as infrared energy, allowing the surrounding gas to lose thermal energy. Additionally, as the cloud becomes denser, its opacity increases, preventing external radiation from penetrating its depths. This creates a thermally insulated environment where cooling continues unabated. When thermal energy diminishes enough, gravity gains the upper hand. Once this collapse begins, internal fragments within the cloud may condense, forming smaller substructures known as dense cores. These cores, cooler and more isolated, are the direct precursors to protostars. The rate and scale of collapse depend heavily on temperature gradients within the cloud. In regions where cooling is more efficient, the collapse proceeds faster, leading to the possibility of forming clusters of stars rather than isolated individuals. This temperature-driven fragmentation is a key factor in determining the mass distribution of stars, a concept known in astrophysics as the initial mass function. The significance of temperature in this context cannot be overstated. Cooler conditions enable the gas to compress more tightly, increasing the likelihood of star formation. In contrast, regions with elevated temperatures resist collapse, remaining stable and starless for much longer spans of cosmic time. This means that the thermal environment of a molecular cloud dictates not only when and where stars will form, but also what kind of stars will emerge. Massive, luminous giants, or small, long-lived red dwarfs. Chemical processes are also influenced by temperature. Cold conditions within the cloud allow molecules such as carbon monoxide, ammonia, and water to form and survive. These molecules are not just passive bystanders. Their rotational and vibrational transitions emit radiation that carries away energy, aiding further cooling. In this way, molecular chemistry and thermal physics operate hand in hand, catalyzing the star-making process. Moreover, astronomers have used temperature-sensitive tracers to map these birthplaces in detail. Instruments such as the Atacama Large Millimeter/Submillimeter Array (ARMA) have detected cold molecular lines that reveal the density, velocity, and thermal history of molecular clouds. These insights have confirmed that the lowest temperatures correspond with the highest likelihood of collapse and star formation. reaffirming the central role of thermal conditions in this cosmic transformation. Historically, the understanding of molecular clouds evolved as observational techniques improved. Early radio astronomy in the mid-20th century detected the signature of neutral hydrogen in the galaxy, but it wasn't until the discovery of carbon monoxide emissions that astronomers could directly observe the cold, dense environments where stars are born. These breakthroughs painted a picture of the galaxy not as a static structure, but as a living, breathing entity where temperature orchestrates cycles of birth and decay. What is perhaps most poetic about this process is the contrast between the extreme cold that initiates the collapse and the intense heat that eventually emerges. The same cloud that starts at mere degrees above absolute zero becomes the birthplace of stellar fire within just a few 100,000 years. A blink in cosmic time, the once cold core begins to radiate, growing brighter as nuclear reactions prepare to ignite. It is a cosmic alchemy, driven by the silent guidance of temperature, transforming gas and dust into luminous orbs that may one day warm planets, power photosynthesis, and become the source of new beginnings. Thus, in the heart of molecular clouds, where light fails to penetrate and silence reigns, temperature acts as the hidden artist, sculpting the very stars that illuminate the universe. It is a tale of opposites, a journey from cold to hot, from dark to radiant, from formless to structured. And, as this transformation continues, it sets the stage for the next great act in the life of a star, the gravitational fall inward, and the heat that swells to challenge it. That rise in internal heat, as gravity compresses matter into tighter bounds, leads us directly into the story of protostellar collapse, where temperature becomes not just a condition, but a force of resistance. And evolution takes its next stride. The thermodynamics of protostellar collapse. In the quiet aftermath of a molecular cloud's disturbance, whether triggered by a supernova shockwave or the gravitational nudge of a passing star, an invisible ballet begins within the densest knots of interstellar gas and dust. What once existed as a tranquil mixture of molecules now trembles with imbalance. Gravity begins to assert its dominance, initiating a slow but inevitable collapse inward. Yet this collapse, so fundamental to the story of star formation, is not merely a matter of mass succumbing to gravity. It is an unfolding thermodynamic transformation governed by energy exchanges that decide whether the birth of a star will ignite or fade. At the heart of this thermodynamic narrative lies a principle as old as physics itself. When a gas compresses under gravity, it heats. This concept, rooted in the first law of thermodynamics, the conservation of energy, dictates that as the gas within the collapsing core contracts, its potential energy does not vanish. Instead, it converts into thermal energy. The temperature of the core climbs steadily, rising from a few degrees above absolute zero to many thousands of degrees Kelvin. The particles within the gas move faster, collisions increase, and pressure begins to mount. This interplay between rising thermal energy and opposing gravitational pull gives the protostar its first signs of inner life. But collapse is never uniform. The center of the core heats and densifies more rapidly than its outer regions. This thermal gradient, subtle at first, becomes the architectural blueprint for the formation of a protostar. As temperatures surge, radiative heat transfer becomes a key player. Photons, scattered and absorbed countless times in the dense core, struggle to escape, trapped by opacity created by dust and ionized particles. This internal bottling of heat means that the interior becomes thermally insulated, driving the temperature even higher, hastening the pace of collapse in the innermost regions while slowing it on the periphery. Thermal pressure, building as a result of heating, attempts to resist further compression. In smaller clouds, this thermal feedback may halt collapse altogether, preventing star formation and dispersing the cloud. But in more massive regions, gravity overpowers pressure, driving the collapse into the next critical phase. These opposing forces, thermal expansion and gravitational compression, are not just mechanical rivals, but thermodynamic counterweights, their equilibrium dictating the fate of embryonic stars. As the core becomes denser and hotter, ionization begins to occur. Hydrogen molecules break apart into atoms, and eventually electrons are stripped from nuclei. This ionization process absorbs energy, temporarily slowing the temperature increase, a phenomenon known as a thermodynamic phase transition. Yet this pause is deceptive. It masks the next evolutionary leap, the moment when heat and pressure become so intense that nuclear fusion becomes inevitable. Amid these changes, convection begins to churn the core. Hotter material rises, cooler gas sinks, and energy is transferred through motion. This convective activity, together with radiative transfer, redistributes heat throughout the forming protostar, leading to a more homogeneous temperature profile. Still, the balance remains fragile. Should the protostar radiate too much heat before nuclear fusion is triggered, collapse may stall, leaving behind a failed star, a brown dwarf. But if conditions are right, the gravitational collapse reaches a critical core temperature of several million degrees Kelvin. At this temperature, protons begin to overcome their mutual repulsion and fuse into helium nuclei, releasing a torrent of energy. This is the fusion threshold, the tipping point at which gravitational energy has been fully converted into thermal energy sufficient to ignite hydrogen fusion. This transformation marks the end of the protostellar phase and the beginning of the main sequence stage of stellar life. From a thermodynamic perspective, this is the moment when the star becomes a self-regulating engine, using outward thermal pressure generated by fusion to counterbalance the relentless inward pull of gravity. Thus, the collapse is not simply a mechanical descent into density, but a tightly choreographed thermodynamic journey. It is a progression from cool molecular whispers to fiery atomic roars. Every step governed by the conversion of gravitational energy into thermal energy. Every delay orchestrated by the subtle complexities of phase transitions and energy transport. The protostar emerges not only as a luminous object, but as a thermal monument to the universe's mastery of equilibrium, transformation, and energy conservation. And yet, the heat within this newborn star is not the end of the thermal story. It is only the ignition. What follows next is a deeper exploration of how this inner fire, born from collapse, becomes the heart of transformation. In the core of the young star, fusion takes over, not just as a source of heat, but as the driver of evolution. And in that blinding crucible, hydrogen will give way to helium, and heat will again become both sculptor and guide. Stellar fusion and heat as a catalyst for transformation. From the crushing pressure and staggering heat of protostellar collapse, a new kind of fire is born. One not kindled by chemical means or external spark, but by gravity's relentless hand compressing atoms into violent intimacy. Deep within the core of a young protostar, As temperature soars to several million degrees, the fundamental nature of matter itself begins to change. This is the dawn of nuclear fusion, the engine of the cosmos, the alchemy of stars, and the furnace in which the universe forges both energy and elements. At its essence, fusion is a process of combination. It defies the usual logic of matter that repels light-charged particles from one another. Protons, positively charged and naturally averse to closeness, are forced together by immense gravitational pressure and the extreme kinetic energy produced by heat. Once close enough, the strong nuclear force, one of the four fundamental forces of nature, takes hold, overpowering the electromagnetic repulsion and binding the particles into a new nucleus. In the early life of a star, this process begins with hydrogen, the universe's simplest and most abundant element. Through a process known as the proton-proton chain, 4 hydrogen nuclei undergo a complex dance of collisions, positron emissions and neutrino production to become one helium nucleus. But what emerges from this transformation is far greater than a mere change in composition. A fraction of the mass of the original hydrogen nuclei is lost in the process. Not destroyed, but converted into pure energy, as described by Einstein's iconic equation, energy equals mass times the speed of light squared. This energy escapes the star's core in the form of high-energy photons, gamma rays, that initiate a long journey outward, scattering and degrading through layers of plasma until they eventually radiate from the star's surface as visible light and heat. This thermonuclear process is not simply a method of illumination, it is the balancing act that sustains the star's life. Fusion generates an outward pressure that perfectly counters the inward pull of gravity, creating a state known as hydrostatic equilibrium. Without it, gravity would continue its collapse and the star would die in its infancy. With it, the star achieves stability, burning steadily, converting matter into energy, and releasing light across the darkness of space. For stars like our Sun, this equilibrium phase lasts billions of years, a testament to the efficient but measured pace of hydrogen fusion. But stellar fusion is more than just balance. It is the great transformer of the cosmos. As hydrogen is slowly consumed, stars evolve. The buildup of helium in the core eventually leads to a new threshold, a new ignition. In more massive stars, once the hydrogen is depleted, the core contracts again, heating to even higher temperatures, initiating helium fusion. In this stage, helium atoms are combined to form carbon, and then through successive stages in increasingly hotter cores, even heavier elements such as oxygen, neon, silicon, and eventually iron. Each step requires higher temperatures and greater pressures, a stairway of elemental creation, powered by gravity's squeeze and heat's transformative power. This fusion sequence is not random. It is structured by the principles of nuclear binding energy. Up to iron, fusion releases energy, making each transformation energetically favorable. But beyond iron, fusion consumes more energy than it releases, marking a boundary in a star's nuclear journey. This is the limit of heat's role as a catalyst in fusion. Beyond it, only the violent deaths of stars, supernovae, can forge the heaviest elements by supplying the enormous energies required to overcome this barrier. From the perspective of thermodynamics, stellar fusion is the controlled release of energy through mass-to-energy conversion. It is not merely a source of heat, but the very engine of transformation that gives the universe its complexity. Every atom of carbon in our bodies, every molecule of oxygen we breathe, was once forged in the core of a star, through these very fusion reactions. Heat, in this context, is not just a byproduct. It is the vital activator, the force that allows the cosmos to climb its own evolutionary ladder. The energy generated in the core also dictates the outer life of a star, its brightness, its temperature, its color, and even its lifespan. More massive stars, though they contain more fuel, burn through it at a ferocious rate, producing more heat and light, but living far shorter lives. Smaller stars, burning slower and cooler, can survive for tens to hundreds of billions of years. The relationship between mass, energy output, and thermodynamic efficiency is finely tuned. Fusion governs not only the existence of stars, but their character, destiny, and influence on their surrounding environments. These fusion-driven stars become cosmic lighthouses, shaping galaxies, nurturing planetary systems, and seeding the interstellar medium with enriched matter. Stellar winds, driven by the heat and radiation pressure from fusion, blow bubbles in space, sculpting nebulae and regulating the formation of future stars. Thus, the heat of fusion does more than preserve a star's life. It sculpts the fabric of the cosmos. Yet, fusion's grip on a star is not eternal. Over time, hydrogen is exhausted, fusion slows, and gravity begins to regain control. The once stable equilibrium starts to wobble, and a new transformation awaits. The next chapter unfolds not in balance, but in instability. In the twilight of a star's life, when the fuel runs low and fusion falters, the balance breaks. What follows is a collapse more violent, a rebirth more dramatic than any that came before. From ashes and iron, the cosmos writes its most powerful verses. An evolution that begins as the stellar core collapses and a dying star prepares to explode. This is where our story now turns, from the calm flame of fusion to the furious chaos of stellar death. Supernovae, thermal triggers of galactic change. Within the blistering furnaces of stellar cores, fusion tirelessly forges heavier elements from lighter ones, sustaining equilibrium for millions or even billions of years. But stars are not eternal. Their stability, delicately balanced between the crushing inward force of gravity and the outward push of thermal radiation, is finite. And when that balance falters, when a massive star exhausts its nuclear fuel, the quiet thermodynamic dance that once nurtured creation gives way to a sudden and violent act of destruction, the supernova. Supernovae are among the most powerful thermal events in the universe. These titanic explosions are born from instability, a critical collapse triggered by the physics of heat, pressure, and the failure of fusion. In the final stages of a massive star's life, when its core becomes rich in iron, nuclear fusion no longer yields energy. Iron cannot fuse into heavier elements without consuming more energy than it releases. At this thermodynamic dead end, the star can no longer resist gravitational collapse. In a matter of seconds, the core succumbs to its own weight, triggering a rebound shockwave of extraordinary intensity. This thermal runaway reaction propels the outer layers of the star into space at velocities exceeding tens of thousands of miles per second, releasing energy that briefly outshines entire galaxies. The temperatures at the core of a supernova can reach over 10 billion degrees, conditions so extreme they facilitate the creation of elements heavier than iron, such as gold, uranium, and platinum. These elements cannot form in the steady, orderly fusion cycles of normal stars. They require chaos, extreme heat, and the sudden acceleration of atomic collisions. Supernovae act as cosmic forges, seeding the interstellar medium with the fundamental ingredients of planets, biology, and future stars. Yet, the influence of supernovae extends far beyond their immediate aftermath. The expelled gas and dust enrich the surrounding galactic environment, becoming the raw material for the next generation of molecular clouds. These remnants serve as both tombstones of a star's death and cradles for stellar rebirth. Shockwaves from supernovae can compress nearby clouds, triggering new waves of gravitational collapse, and thus sparking fresh star formation. This self-propagating chain of destruction and creation marks supernovae not as ends, but as catalytic events in the grand thermodynamic cycle of the cosmos. Thermally, a supernova also represents an ultimate release of stored stellar energy. Over its lifetime, a star builds up internal pressure through nuclear fusion, bottling heat deep within its core. When that energy is abruptly unleashed, it reshapes the galactic landscape. The expanding remnants of a supernova can persist for tens of thousands of years, growing into vast nebulae that emit in X-ray, ultraviolet, and visible light. These glowing clouds are not only beautiful, but serve as markers of thermodynamic history. Records of pressure gradients, chemical abundances, and thermal energy transfer on cosmic scales. In human terms, the study of supernovae offers both existential and scientific insight. The iron in our blood, the calcium in our bones, the iodine in our thyroid. None of these could exist without the thermonuclear crucible of a dying star. Every atom heavier than helium owes its existence to thermal instability and explosive change. In this way, the temperature thresholds reached in supernovae are not just violent outbursts of energy, they are the very pathways through which matter transforms and evolves. Across the observable universe, supernovae continue to shape galaxies. Some explode in relative isolation. Others occur in tightly knit stellar neighborhoods, triggering chain reactions of activity. In both cases, they demonstrate the profound effect of thermal disequilibrium in large-scale structure. They challenge the notion of permanence and underscore that even stars, long considered symbols of constancy, are subject to the universal law of thermodynamic change. The universe remembers their deaths not as silent voids, but as radiant legacies of heat and matter. As we move deeper into the architecture of cosmic bodies, we find that the aftershocks of stellar death ripple into the formation of planets. The next phase in our exploration of thermal influence leads us to examine how variations in heat sculpted the solid worlds of solar systems. Their textures, layers, and boundaries, born from gradients of temperature within the primordial disks that formed them. Temperature differences in planetary formation. In the wake of a supernova's incandescent demise, the interstellar medium becomes rich with heavy elements, stirred and compressed by powerful shockwaves. This chaotic, energized environment lays the groundwork for the next act in the cosmic cycle, the birth of planets. At the center of this transformation lies a principle both elegant and fundamental: temperature gradients. It is not uniformity that sculpts worlds, but difference, and in the swirling protoplanetary disks around young stars, the variance in temperature becomes the sculptor of planetary architecture. A newborn star forms at the heart of a collapsing molecular cloud, and around it gas and dust begin to flatten into a rotating disk. This protoplanetary disk is not a monolithic structure, but a highly dynamic, thermally stratified region where temperatures vary drastically with distance from the central star. Closest to the star, the heat is intense, hot enough to vaporize volatile compounds and even melt rock. Farther out, The environment cools, allowing ices to condense and more delicate compounds to remain stable. This thermal zoning, governed by the laws of radiation and thermodynamics, is responsible for the great diversity of planets we observe, both within our solar system and beyond. In the inner regions of the disk, where temperatures soar above the melting points of metals and silicates, only the most refractory materials can survive. Here, the building blocks of terrestrial planets like Mercury, Venus, Earth, and Mars coalesce. These rocky bodies are composed primarily of iron, nickel, and silicate minerals, all forged in the hot crucible of the disk's interior. Their formation is a process of accretion, where microscopic grains collide, stick, and gradually grow into planetesimals and protoplanets, all under the influence of heat-driven dynamics and gravitational interactions. Meanwhile, beyond a critical boundary known as the frost line, or snow line, the disk cools sufficiently for water, methane, ammonia, and other volatiles to condense into solid ices. In these colder regions, accretion proceeds with a different set of ingredients. Ices, being more abundant than metals and rocks, allow for the rapid formation of massive cores, which in turn can attract thick envelopes of hydrogen and helium from the surrounding gas. Thus are born the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, whose compositions reflect the thermal realities of their birthplace. It is this thermal frontier that divides rocky worlds from gas-dominated giants, shaping not only their physical characteristics, but also their orbital distributions and internal structures. The effect of temperature extends beyond composition. It also determines the timeline and efficiency of planet formation. High temperatures near the star drive faster chemical reactions and more rapid dust processing, yet they also generate turbulence and instabilities that can inhibit the growth of large planetary bodies. Cooler outer regions, while chemically rich and less violent, suffer from slower growth rates due to the lower collision speeds and reduced density of solid material. Thus, the interplay between heat and time crafts distinct planetary types through divergent pathways, all rooted in the initial thermal map of the disk. Moreover, isotopic studies of meteorites, some of the oldest remnants of the early solar system, reveal a complex thermal history. These space rocks preserve chemical fingerprints of rapid heating events, such as shockwave processing and short-lived radionuclide decay, which further influenced the temperature structure of the disk. These brief yet powerful heating events altered mineralogy and helped differentiate materials, ensuring that even within the same region, planetary precursors could diverge in composition and destiny. Temperature gradients also influence planetary migration. As nascent planets interact with the gas and dust of the disk, they can shift inward or outward, depending on local thermal conditions. This movement, known as planetary migration, is driven by subtle forces that arise from density waves in the gas, and it has a profound impact on the final architecture of planetary systems. In many observed exoplanetary systems, gas giants are found close to their stars, hot Jupiters, suggesting a dynamic process of inward migration that likely originated in the cooler outer disk before being drawn inward by thermal and gravitational forces. Even after formation, thermal dynamics continue to shape planetary evolution. Internal heat, often retained from accretion or generated by radioactive decay, drives geological activity. Volcanism, tectonics, and magnetic fields. External heating from the star determines climate, atmospheric retention, and surface chemistry. In short, Temperature is not only the architect of planetary birth, but also the regulator of planetary life cycles. The contrast in thermal environments between different regions of the disk ensures that no two planets are identical. The gas giants, with their swirling storms and deep hydrogen envelopes, the icy dwarfs of the Kuiper Belt cloaked in frozen methane, the airless scorched rock of Mercury, and the habitable blue marble we call Earth, all are manifestations of temperature-dictated assembly. Heat shapes mass, orbits, chemistry and atmosphere, playing a central role in the grand story of planetary diversity. And as we now peer outward into other planetary systems with telescopes like the James Webb Space Telescope and space missions like TESS, we see this thermal pattern repeated across the galaxy. Systems form with rocky worlds inside, gaseous giants outside, and strange anomalies in between. The logic of heat, of differences in temperature across circumstellar space, proves itself universal, fundamental, and enduring. With the structure of planets dictated by thermodynamics, the next chapter in our exploration turns to how these planetary bodies store and radiate heat, how thermal inertia, conductivity, and internal pressure define planetary interiors and energy cycles. From their crust to their cores, planets reveal the continuing legacy of the heat that made them. Beneath the outer reaches of the solar system, where light barely glimmers and temperatures plummet to realms colder than any desert night on Earth, lie some of the most active and geologically dynamic bodies in the cosmos. These are the icy moons, enigmatic satellites that orbit gas giants like Jupiter and Saturn. At first glance, they seem frozen in ancient crusts of water ice, their surfaces scarred by impact craters and mysterious streaks. Yet, deep below these frozen exteriors, something remarkable is happening. The story of these worlds is not one of silence and stagnation, but of heat and motion, of volcanic plumes and shifting crusts. An inner revolution driven by the most fundamental force in the cosmos: temperature. While terrestrial planets like Earth generate tectonic activity through the decay of radioactive elements and the gradual cooling of their molten interiors, icy moons rely on more subtle, yet equally powerful mechanisms. Chief among them is tidal heating, a process born from the complex gravitational ballet between moons and their parent planets. As moons like Europa, Enceladus, and Ganymede orbit massive gas giants, their paths are tugged and stretched by gravitational forces, causing internal flexing that generates frictional heat. This heat does not escape easily. Instead, it builds up deep within, melting ice into hidden oceans and fueling volcanic activity beneath miles of frozen crust. On Jupiter's moon Europa, evidence of this internal heat has transformed scientific expectations. Its surface is crisscrossed with reddish-brown lines, tectonic fractures where ice plates have shifted, buckled, and broken apart. These features are eerily similar to Earth's mid-ocean ridges, suggesting active geological processes beneath the surface. More compelling are hints of cryovolcanism, the eruption not of molten rock, but of slushy water, salts, and possibly organic compounds, forced up through fractures in the icy shell. These icy eruptions are powered by the same heat that churns Europa's subsurface ocean, making it a prime candidate in the search for extraterrestrial life. Farther out, Saturn's moon Enceladus offers one of the most vivid displays of heat-fueled geological activity in the outer solar system. In 2005, NASA's Cassini spacecraft captured stunning images of geyser-like plumes erupting from the moon's south pole. These plumes, composed of water vapor, ice particles, and organic molecules, shoot hundreds of miles into space, originating from fractures known as tiger stripes. What makes Enceladus particularly compelling is the amount of energy required to sustain these plumes over time. Scientists have calculated that the internal heat driving this activity must be substantial and sustained, likely through a combination of tidal flexing and possibly even radioactive decay. Beneath its icy shell, Enceladus harbors a global ocean, kept warm by this internal energy, hinting again at the potential for life in an otherwise frozen realm. Even larger moons like Ganymede and Titan reveal the influence of internal heating on a grand scale. Ganymede, the largest moon in the solar system, possesses a magnetic field, a feature that implies a partially molten convecting core. This suggests that even in the far reaches of the solar system, heat can persist long after the moon's formation, shaping magnetic and geological structures. Titan, Saturn's massive haze-shrouded moon, boasts rivers, lakes and seas of liquid methane and ethane on its surface, but its interior holds a different secret. Evidence points to a subsurface ocean kept warm by a combination of heat sources, including tidal friction. These hidden oceans, liquid and dynamic beneath miles of ice, are a testament to the quiet persistence of thermal energy. In each of these worlds, the narrative of temperature shifts from the realm of star formation and galactic cataclysm to one of subtle, long-term geological change. Heat becomes the hidden engine beneath icy mantles, the silent architect of fractures, plumes, and possible habitats. This reshaping of icy moons has forced planetary scientists to rethink the conditions necessary for geological activity. And, perhaps more importantly, for life itself, where once it was believed that a planet must be close to a star to remain active, the discovery of thermally dynamic moons has expanded the boundaries of habitability. But the story of temperature does not stop at plumes and oceans. From icy shells to heated cores, from subterranean oceans to surface reshaping, temperature continues to guide the evolution of planetary systems. And it leaves traces, not just in fractures or geysers, but in the very echoes of the Big Bang. As we turn our attention away from these frozen moons and look outward once again, we encounter a different kind of thermal footprint, one written across the entire sky, whispering the story of the cosmos itself. It is the residual glow from the birth of everything. The cosmic microwave background, the next stage in our journey through the silent transformation of heat. Long after the last geyser has fallen silent on Enceladus, and Europa's subsurface tides have grown still beneath thickening crusts of ice, a deeper, more ancient warmth continues to echo across the cosmos, one that has nothing to do with volcanic activity or tidal flexing. It is not bound to a planet or moon, nor does it rise from a molten core. This warmth is everywhere. It permeates the fabric of space itself, invisible to the naked eye, yet detectable by instruments tuned to the faintest whispers of the universe's past. This omnipresent glow is the thermal memory of creation. It is the cosmic microwave background, a silent ghost of the universe's birth, still glowing after more than 13 billion years. To understand the cosmic microwave background, or CMB, one must journey back to a time when the universe was not a sprawling expanse of galaxies and voids, but a compact, seething fireball of energy. In the beginning, matter and radiation were locked in a chaotic dance. Too hot and dense for atoms to form, too turbulent for light to escape. This opaque plasma, made of free electrons and protons, scattered every photon in every direction. The universe, in this early state, was bright but blind, glowing like the interior of a star, yet invisible from within. It was only as the universe expanded and cooled, driven by the relentless stretch of space-time itself, that a crucial threshold was reached. Roughly 380,000 years after the Big Bang, temperatures finally dropped low enough for electrons to combine with protons, forming neutral hydrogen atoms. With the electrons no longer free to scatter light, photons could travel unhindered for the first time. The universe became transparent, and the light released in that instant began its long journey through space. That light has never stopped traveling. Stretched by the expansion of the universe, those primordial photons have shifted into the microwave region of the electromagnetic spectrum. What was once a brilliant blaze now exists as a cold, uniform afterglow, measurable at a temperature just above absolute zero. It is a near-perfect blackbody spectrum, smooth and consistent in every direction, with faint fluctuations that reveal the seeds of all future cosmic structure. This radiation is not a relic of a star or a galaxy, but of the entire cosmos at its infancy. It is the universe's thermal ghost, imprinted across the sky. The first hints of this ancient light were not discovered with purpose, but by accident. In the mid-1960s, two American radio astronomers, Arno Penzias and Robert Wilson, were calibrating a sensitive microwave antenna in New Jersey when they encountered a persistent background noise. It came from no known source on Earth, no star, no galaxy. It was uniform, ever-present, and impossible to eliminate. They had stumbled upon the CMB, confirming a key prediction of the Big Bang theory and forever altering our understanding of cosmic history. For this, they received the Nobel Prize in Physics, and cosmology moved from speculation to precision science. Over the decades that followed, increasingly sensitive instruments mapped the CMB with greater clarity. NASA's COBE satellite, launched in the early 1990s, revealed tiny temperature differences across the sky, ripples only millionths of a degree apart. These slight variations were cosmic fingerprints, representing density fluctuations in the early universe that would later grow into galaxies and clusters of galaxies. COBE's findings were refined by subsequent missions such as WMAP and Planck, which mapped the microwave sky with unprecedented resolution. These observations have given cosmologists a detailed picture of the universe's age, composition, and shape. The CMB tells us that the universe is not only expanding, but accelerating in that expansion, driven by a mysterious force known as dark energy. It reveals that ordinary matter, the kind that makes up stars, planets, and people, is a mere fraction of what exists. Most of the cosmos is composed of invisible forms of matter and energy, detectable only through their gravitational effects. These insights have not only deepened our understanding of where we come from, but have reshaped the very questions we ask about the universe's fate. And yet, for all its revelations, the CMB remains curiously silent about certain fundamental mysteries. It hints at phenomena that occurred even before light was able to travel freely, such as cosmic inflation, a rapid exponential expansion of the universe in its first moments, far faster than the speed of light. Inflation would have smoothed out the fabric of space, explaining the CMB's incredible uniformity, while also seeding the tiny quantum fluctuations that grew into galaxies. But inflation itself is still a theory, supported by indirect evidence and awaiting deeper observational confirmation. There are also anomalies, subtle irregularities in the CMB data that challenge our expectations. One region of the sky appears unusually cold. Some maps suggest a slight asymmetry in the CMB's temperature distribution. Are these signs of undiscovered physics? Are they statistical flukes or hints of parallel universes brushing against our own? The CMB, while largely uniform, contains just enough imperfection to stir the imagination of physicists and philosophers alike. Yet above all else, the cosmic microwave background reminds us of something profound, that the universe has a memory. The light released at the moment transparency began has never faded completely. It surrounds us still, invisible but ever-present, a soft whisper from the moment time became legible. Every star, every planet, every molecule in your body exists against this faint thermal backdrop, a silent chorus singing the birth of space and time. But just as this ancient radiation illuminates the past, it also frames the next question. If the universe still carries the thermal imprint of its birth, what becomes of all this energy in the far future? When the last stars have burned out, when galaxies drift into darkness, and when heat itself begins to vanish, what remains then? As we follow the trail of cosmic temperature ever forward, we encounter a horizon of unimaginable stillness, a final equilibrium where all thermodynamic processes cease. In this ultimate silence we glimpse the cold end of everything, the universe's thermal death, thermonuclear reactions in neutron stars. From the primordial fireball to the haunting echoes of the cosmic microwave background, the journey of thermal energy has shaped the grand architecture of the cosmos. But nowhere is the intensity of this energy more extreme and more transformative than within the hearts of neutron stars. Cosmic furnaces born from the death throes of massive suns, where thermonuclear reactions occur under unimaginable conditions. As we now plunge into the densest thermal crucibles known to exist, the narrative turns from ancient echoes to present fire, from spectral ghosts to nuclear fury. In the long chronology of cosmic evolution, neutron stars represent a paradox wrapped in gravity. Objects so small, yet so incredibly dense, that a single teaspoon of their matter would weigh billions of tons. They emerge not from gradual accumulation, but from sudden cataclysmic collapse, specifically the remnants of supernovae, where a once massive star's core implodes under the crushing weight of gravity. The resulting neutral star is just about a dozen miles wide, yet its mass rivals that of an entire sun. Inside this compressed remnant, the laws of matter bend. Quantum mechanics intertwines with gravitational extremes, and thermonuclear energy finds its most brutal and brilliant expressions. The very formation of a neutron star is a thermal and kinetic upheaval. As the core collapses, protons and electrons are squeezed into neutrons, a process that releases a flood of neutrinos, ghostly particles that carry away a significant portion of the gravitational energy. What remains is a compact, spinning furnace, whose outer layers are still heated to temperatures exceeding 100 billion degrees at birth. Over time, the surface cools, but the internal dynamics remain anything but quiet. The immense gravity crushes atomic structures, creating a layered structure, an atmosphere barely a few centimeters thick, a crust of neutron-rich nuclei, and beneath it, a core where neutrons, protons, and exotic particles interact under forces that defy replication on Earth. At the heart of this structure lie thermonuclear reactions that push physics to its limits. Unlike the standard hydrogen fusion in stars like our Sun, neutron stars exhibit a much more exotic suite of nuclear processes. One of the most dramatic is the phenomenon of nuclear burning on the surface of accreting neutron stars. those that exist in binary systems and siphon matter from a companion star. As this material, primarily hydrogen and helium, accumulates on the star's surface, it forms a thin, dense envelope. When conditions become right, this envelope undergoes a sudden, runaway thermonuclear reaction. The result is an X-ray burst, an explosive release of energy that for a brief moment can outshine an entire galaxy in the X-ray spectrum. These X-ray bursts are the neutron star's equivalent of stellar flares, but they operate at scales and intensities that dwarf anything found in conventional stellar environments. The underlying reactions include rapid proton capture processes, known as the RP process, in which nuclei rapidly absorb protons and undergo beta decays, forming heavier elements in mere seconds. This is not a gentle simmer, but a violent, brief conflagration in which atomic nuclei are forged and destroyed at breakneck speed, producing elements like selenium, krypton, and even tellurium, all from the chaotic dance of nuclear particles on a layer thinner than a piece of paper. Beyond these surface phenomena, theorists believe that even deeper within the star's core, under crushing pressure and searing temperatures, more exotic states of matter may emerge. One hypothesis suggests the formation of quark-gluon plasma, a primordial soup of subatomic particles that existed only moments after the Big Bang. In such an environment, thermodynamic laws play out in wholly unfamiliar ways. Thermal conductivity, viscosity, and heat capacity no longer behave according to classical expectations, but are dictated by quantum chromodynamics, the theory that governs the strong nuclear force. Some neutron stars, known as magnetars, exhibit even more intense thermodynamic properties. Their magnetic fields are trillions of times stronger than Earth's, capable of distorting atomic orbitals and even the vacuum of space itself. These magnetic fields can generate enormous thermal gradients, leading to powerful starquakes and bursts of gamma radiation. When a magnetar flares, it releases more energy in a single moment than our Sun does over hundreds of thousands of years. These bursts are not merely thermonuclear, they are thermomagnet dynamic, representing a fusion of thermal, nuclear, and magnetic forces so powerful that they remain only partially understood. Yet despite their extremity, neutron stars are also cosmic laboratories. Their thermonuclear processes, detectable through X-ray and gamma-ray telescopes, provide insight into the behavior of matter under conditions that cannot be recreated on Earth. From the burst profiles and decay curves of X-ray transients, scientists can infer the composition of the accreted material, the rate of nuclear burning, and even the equation of state of ultra-dense matter. Every flare, every pulse, and every thermal ripple from a neutron star tells a story, written in the language of high-energy thermodynamics. These observations are not just esoteric. They influence models of nucleosynthesis, how the universe makes elements. They refine our understanding of fundamental forces. They even help us understand the thermal evolution of the universe itself, for neutron stars act as thermal lighthouses, keeping time with the cosmic clock as they cool slowly over millions of years. The interplay of heat, gravity, and quantum force within their tiny radius is a mirror of the greater forces shaping the cosmos, compressed into a sphere the size of a city. And so, the tale of heat and thermodynamics, having begun in the distant fire of the Big Bang, travels through protostars, stellar cores, supernovae, planetary disks, and icy moons, only to converge in the furious interior of a neutron star, a beacon of nuclear fire that burns not for life, but for revelation. Yet even this is not the end. As neutron stars cool and fade or spiral into black holes through binary mergers, their thermal legacy continues. In their collapse, they release gravitational waves and forge heavy elements through kilonovae, marking the next frontier in our journey. This brings us forward not to an end but to another stage in the thermodynamic cycle of the universe, where gravity, heat, and radiation join again in stellar remnants, deepening the cosmic tapestry. And as neutron stars die or merge, another silent witness begins to dominate the stage: black holes, where heat disappears behind an event horizon and entropy reaches its pinnacle. In the next chapter, we explore this ultimate threshold, where temperature, time, and light itself cease to behave as we know them. Black-body radiation and stellar temperature profiles. From the glowing embers of campfires to the radiant hearts of stars, heat reveals its presence through light. In the vast realm of astrophysics, this relationship between heat and light is formalized through a concept both elegant and essential: black-body radiation. This phenomenon, defined by the emission of electromagnetic radiation by an idealized object that absorbs all incident energy, serves as a thermal fingerprint for understanding stars. Every star in the sky, from the nearest red dwarfs to the blazing blue giants on the outer fringes of the Milky Way, tells its story through the light it emits. At the foundation of this cosmic storytelling lies black-body radiation, an anchor that allows astronomers to read the thermal histories and present states of stellar bodies with astonishing precision. A black body is not merely theoretical. It provides a benchmark, a standard model of how objects should emit radiation solely due to their temperature. When a star behaves closely to this model, its emitted spectrum can be analyzed with remarkable accuracy to determine its surface temperature. This relationship, codified through Planck's law, Stefan Boltzmann law, and Wien's displacement law, allows scientists to unravel the internal physics of stars by simply observing their light. The Stefan Boltzmann law, for instance, reveals that a star's luminosity is directly proportional to the fourth power of its surface temperature, showing that even a slight increase in temperature can produce a dramatic increase in energy output. Through this lens, stars are no longer anonymous points of light. A red star, with its cooler surface temperature, radiates most of its energy in the infrared and red portions of the spectrum. In contrast, a blue star, with a significantly hotter surface, shifts its peak emission toward the ultraviolet. This gradient across the color spectrum is not just a visual cue, it is a thermal roadmap. The spectrum of a star serves as its identity, revealing not only its current temperature, but also its age, chemical composition, and evolutionary stage. Black-body radiation also provides the framework for understanding stellar classification. The Hertzsprung-Russell diagram, a cornerstone of modern stellar astrophysics, is built upon temperature and luminosity, both rooted in black-body principles. This powerful tool categorizes stars into main sequence: giants, supergiants, and white dwarfs, revealing patterns of life cycles driven by thermal physics. For example, white dwarfs, though faint in luminosity, are often blisteringly hot, radiating mainly in the ultraviolet. Their dim appearance is not a matter of temperature, but of surface area, underscoring that stellar brightness cannot be interpreted without a nuanced understanding of both radiation and size. Perhaps one of the most fascinating applications of black-body radiation lies in the cosmic dance between matter and energy in stellar atmospheres. Here, the interplay of thermal energy with atomic structures results in absorption lines. Dark bands imprinted onto the otherwise continuous spectrum. These lines are more than gaps in color. They are signatures of the elements within a star's atmosphere, altered by thermal motion and pressure. Through this, astronomers can identify the chemical makeup of a star across vast distances, revealing, for instance, whether it harbors heavy elements synthesized in previous generations of stars or formed in relative isolation from galactic evolution. Moreover, black-body radiation bridges the understanding between different types of celestial objects. A neutron star, with a temperature that may reach into the millions of degrees, emits most of its energy in X-rays, while planets, much cooler by comparison, radiate primarily in the infrared. The same black-body framework that allows us to measure the gentle warmth of Earth's surface enables us to interpret the fierce energies of pulsars, or the cold echoes of distant exoplanets. In the realm of observational astronomy, instruments like spectrometers and photometers rely entirely on black-body principles. Whether mounted on ground-based observatories or orbiting Earth aboard telescopes like Hubble or the James Webb, these instruments decode the light of the universe into temperature maps, atmospheric signatures, and stellar ages. The elegant simplicity of black-body radiation provides a universal translator across the cosmos, turning heat into light and light into knowledge. Black-body curves are not fixed. They shift depending on temperature, moving their peaks and stretching or compressing their wavelengths. This dynamic nature allows scientists to track changes over time. A cooling star, for instance, will gradually move its emission peak toward longer wavelengths, dimming its blue and brightening its red. These subtle shifts are keys to understanding stellar evolution, the transition from one phase to another, and the slow march towards stellar death. As we approach the deeper realms of astrophysical complexity, the trail illuminated by black-body radiation leads toward the vast clusters of galaxies and the behavior of temperature across gravitational structures. From the thermal pulse of an individual star to the searing radiation of entire galactic formations, the spectrum of light becomes an archive of motion, energy, and entropy. This journey now transitions toward exploring the kinetic energy and internal temperatures that ripple through massive galactic clusters. Regions where individual stars no longer tell the story alone, but instead entire galaxies dance to the rhythm of thermodynamic forces. Thermal evolution of white dwarfs. As the fires of a star's core begin to dwindle, a quiet transformation takes place, one that strips away the brilliance of a main sequence life and ushers in the solemn stillness of a white dwarf. This metamorphosis is not a collapse into darkness, but a slow, graceful fading from heat into cold. The white dwarf, though seemingly modest in its radiance, is a crucible of ancient heat and condensed history. Its thermal evolution from a blazing remnant to a cold and silent object is one of the most profound and telling narratives in stellar astrophysics. White dwarfs are not born in explosive chaos, but in the aftermath of stellar equilibrium. When stars like our Sun exhaust their nuclear fuel, fusion halts in their cores. Gravity begins to dominate, pulling the core inward. But rather than collapsing endlessly, the core reaches a unique state known as electron degeneracy pressure, a quantum mechanical effect that resists further compression. It is this resistance, not energy from fusion, that supports a white dwarf against gravitational collapse. In this state, the star becomes incredibly dense, often packing a mass comparable to the Sun into a volume no larger than Earth. The intense temperatures generated during the red giant phase remain trapped inside, with no mechanism to renew the heat. From this point forward, a white dwarf becomes a thermal relic, a slowly cooling ember drifting through time. Initially, the surface temperature of a new white dwarf can soar to hundreds of thousands of degrees Kelvin. This heat radiates outward, mostly in ultraviolet wavelengths, making young white dwarfs searingly bright in specific spectral bands. However, unlike stars on the main sequence, white dwarfs lack an internal engine. No new energy is being produced. All thermal radiation comes from residual heat left over from their earlier life. As a result, the cooling process is inevitable and irreversible. This marks the beginning of their long descent down the so-called white dwarf cooling curve. The rate of cooling is dictated by several intricate factors. First, the thermal conductivity of the white dwarf plays a critical role. Its core, composed primarily of carbon and oxygen, conducts heat efficiently. The degenerate electrons move freely, rapidly transferring energy from the interior to the outer layers. But this very efficiency causes the surface to cool faster, radiating heat into space and lowering the overall temperature. As the surface temperature decreases, so does the luminosity, following a path that is well modeled, but deeply tied to the physics of dense matter. Second, the mass and composition of the white dwarf determine how fast it loses its heat. More massive white dwarfs, although having stronger gravity and smaller radii, tend to cool more slowly because they store more internal energy. Less massive ones, while larger in volume, have lower central temperatures and shorter thermal lifetimes. Composition also plays a subtle but crucial role. If a white dwarf contains traces of hydrogen or helium in its outer layers, these elements can form insulating blankets, slowing the rate of cooling. In contrast, a bare carbon-oxygen surface loses heat more readily, accelerating its transition into a colder, dimmer state. The most fascinating phase of white dwarf cooling emerges in the crystallization process, a transformation once thought impossible on stellar scales. As the white dwarf cools to around several thousand degrees Kelvin, the dense carbon and oxygen ions begin to organize into a crystalline lattice. This is not merely a drop in temperature, it is a profound structural phase change. The star's interior begins to solidify, similar in principle to how water freezes into ice, but under conditions of unimaginable pressure and density. During crystallization, latent heat is released, temporarily slowing the cooling process. This latent energy acts as a final breath of warmth, delaying the star's descent into complete darkness. In recent years, the European Space Agency's Gaia mission provided evidence of this phenomenon by observing a population of white dwarfs clustered around a specific luminosity, a thermal plateau caused by crystallization. As cooling continues beyond the crystallization phase, the white dwarf enters a stage where it emits primarily in the infrared. Its once brilliant glow becomes faint and hard to detect. This twilight period may last for trillions of years, far longer than the current age of the universe. In theory, if given enough time, a white dwarf will continue to cool until it reaches thermal equilibrium with the cosmic microwave background radiation. At that point, it would become a black dwarf, a theoretical object so cold it emits no light at all. However, since the universe is only around 13 billion years old, no black dwarfs are thought to exist yet. They remain a prediction of the far future, a glimpse into the ultimate fate of matter after stars have ceased to shine. Beyond the elegance of this cooling process lies a deeper utility. Because white dwarfs cool in a predictable fashion, they serve as cosmic chronometers. By measuring the temperature and luminosity of a white dwarf, astronomers can estimate its cooling age, the time since it became a white dwarf. In stellar clusters, where all stars form roughly at the same time, this allows researchers to determine the cluster's age with remarkable precision. This method has been used to date some of the oldest star clusters in the Milky Way, refining our understanding of galactic history and the chronology of star formation. Additionally, the study of white dwarf evolution informs models of dark matter and alternative physics. Certain cooling anomalies have led researchers to speculate about interactions with weakly interacting particles, such as axions, hypothetical particles that could explain dark matter. If white dwarfs cool faster than models predict, it could hint at unknown processes radiating energy from their interior. Thus, even in their silence, white dwarfs may be whispering secrets about the fundamental nature of the universe. Thermal evolution does not occur in isolation. Some white dwarfs reside in binary systems, where mass transfer from a companion star can dramatically alter their thermal history. Accreting material can reignite nuclear fusion on the surface, triggering novae, sudden outbursts that temporarily brighten the star and reset the cooling clock. In more extreme cases, runaway accretion can lead to a Type Ia supernova, completely unbinding the white dwarf and dispersing its matter across space. Thereby, these violent episodes complicate the cooling process, but also provide a mechanism for enriching galaxies with heavy elements and calibrating cosmological distances. The slow march of a white dwarf from a blazing core to a cold remnant embodies the universe's deep entropic pull. It is a story of residual energy, of resistance against complete darkness, and of the long, quiet life that follows the death of a star. It reminds us that even in silence, there is structure. Even in cooling, there is order. And even in the absence of nuclear fire, there is a timeline to be read, understood, and used as a beacon across the cosmos. As we now step away from the quiet solitude of white dwarfs, our focus shifts to a grander scale, one that involves not isolated stars but entire galaxies, held together by invisible threads of gravity. The internal motion and kinetic interactions within these colossal systems offer the next chapter in understanding the universe's evolving thermal landscape. The study of velocity fields in expanding galaxy clusters reveals how motion itself sculpts temperature distributions across cosmic structures. In the vastness of the solar system, far beyond the temperate zone that cradles Earth's familiar climate, lie the majestic gas giants, Jupiter, Saturn, Uranus, and Neptune. Though these worlds are cold by terrestrial standards, bathed in only a fraction of the sun's warmth, they are anything but inactive. Their skies swirl with storms of unrelenting fury, their bands churn with titanic winds, and their poles host auroras that dance with ethereal light. At the heart of this dynamic chaos is a force that seems paradoxical at first: heat. In realms where sunlight barely warms the clouds, it is heat from within, and the laws of thermodynamics that sculpt some of the most extreme weather phenomena in the known universe. To understand heat-driven weather patterns on gas giants, one must first abandon Earth-centered thinking. On Earth, the sun is the dominant engine of atmospheric motion. Solar radiation warms the equator more than the poles, creating pressure differences and driving winds and jet streams. Weather in this context is largely the result of external heating, but on gas giants, particularly Jupiter and Saturn, it is the internal heat, residual energy from their formation and ongoing gravitational contraction, that far outweighs the influence of the distant Sun. Jupiter, for example, emits nearly twice as much energy as it receives from solar radiation. Saturn, too, radiates significantly more heat than it absorbs. These planets are not just passive recipients of light, they are thermal engines unto themselves. The source of this internal heat traces back to the early formation of the planets. During accretion, as vast quantities of gas and dust collapsed under gravity to form these giants, the gravitational potential energy was converted into thermal energy. Over billions of years, this heat has been slowly leaking out, a process called Kelvin-Helmholtz contraction. As their massive atmospheres continue to settle and compress under their own weight, they release latent heat that drives convection, rising and sinking motions in the planetary fluid layers. This convection fuels the belts and zones, those contrasting light and dark bands etched across the faces of Jupiter and Saturn. These bands are not merely colored clouds. They are manifestations of powerful jet streams flowing at hundreds of miles per hour, all directed by the way heat escapes from the planet's depths. On Jupiter, the most iconic symbol of heat-driven weather is the Great Red Spot, a colossal anticyclone large enough to swallow Earth whole. This storm has persisted for at least 4 centuries, perhaps longer. Its longevity and energy are sustained by the continuous upwelling of heat from below, interacting with the planet's rapid rotation to form a vast, stable vortex. The planet's rotation is key. Spinning once every 10 hours, Jupiter generates immense Coriolis forces that twist convective flows into tightly organized bands and storms. Saturn, though more visually subdued in visible light, exhibits similarly extreme dynamics. Beneath its pastel clouds rage storm systems that span the entire planet. Every few decades, a storm known as the Great White Spot erupts in Saturn's northern hemisphere. It is believed to be caused by seasonal cooling and warming in the upper atmosphere, driven by both internal heat and changes in solar insolation. Unlike Earth's brief thunderstorms, these planetary-scale eruptions can last for months or even years, disrupting existing weather systems and reshaping entire cloud bands. Further afield, the ice giants, Uranus and Neptune, present a different thermal puzzle. Uranus is an anomaly. Despite being massive, it emits almost no excess heat, leading to a frigid and sluggish atmosphere with subdued weather features. Why Uranus lacks significant internal heating remains a mystery. Some hypotheses suggest a past collision might have disrupted its core, or caused its internal heat to be trapped. Neptune, by contrast, is nearly as cold as Uranus, but boasts far more dramatic weather, including the fastest winds in the solar system, exceeding 1,000 miles per hour. Neptune emits nearly twice as much energy as it receives from the Sun, indicating a robust internal heat engine that, combined with the planet's composition and dynamics, fuels these extreme atmospheric motions. These gas and ice giants also exhibit layered atmospheres, with different gases condensing and interacting at various altitudes depending on pressure and temperature. Ammonia, hydrogen sulfide, water vapor, and methane form clouds at different depths, and the way heat percolates through these layers influences where storms form and how energy is distributed. Lightning detected on Jupiter and Saturn suggests vigorous convective activity, further reinforcing the role of rising heat in shaping the weather systems. Another crucial factor in these weather patterns is vertical heat transport. On gas giants, the lack of a solid surface allows for deep atmospheric circulation. Hot gas from the interior rises, cools as it ascends, and sinks again, creating a powerful convective engine. These vertical motions interact with horizontal wind shears, resulting in complex three-dimensional flows that differ vastly from Earth's relatively shallow atmospheric motion. Moreover, the magnetic fields of Jupiter and Saturn add another layer of complexity. These fields interact with charged particles and create auroras that, while visually stunning, are also indicators of how internal heat and magnetic forces work in tandem to structure the upper atmosphere. On Earth, auroras are mainly solar-driven, but on Jupiter, much of the auroral activity is powered by the planet's own rotation and magnetic field dynamics. In recent decades, spacecraft missions such as Voyager, Galileo, Cassini, and Juno have provided breathtaking insights into these colossal weather machines. Juno's microwave radiometer has penetrated deep beneath Jupiter's cloud tops, revealing that its iconic bands extend thousands of miles into the planet's interior, driven by convective processes linked to internal heat. Cassini, orbiting Saturn for over a decade, captured the hexagonal storm at the North Pole, a baffling geometric feature possibly stabilized by standing waves in the atmosphere, again influenced by heat flows and rotational dynamics. Altogether, heat on gas giants does not simply dissipate, it sculpts. It sculpts the bands, the storms, the jet streams, and even the seasons. These planets are not frozen or dead. They are alive with a physics all their own, powered not by the light of their distant star, but by the seething energy trapped within their cores. And as we trace the journey of heat across these massive worlds, we begin to understand a cosmic principle that stretches far beyond planetary weather. Heat, how it moves, transforms, and interacts with gravity and matter, becomes a unifying thread, not just in atmospheres, but in galaxies, stars, and the very structure of the universe itself. As we leave the swirling clouds of gas giants behind, our attention now turns to regions where heat behaves not in storms, but in the motion of entire clusters of galaxies, where matter itself flows and stretches space in colossal fields of velocity, tracing the universe's grand expansion. In the vastness beyond our solar system, orbiting stars, both familiar and foreign, lie a staggering number of worlds known as exoplanets. These distant planets, once theoretical, are now becoming observable thanks to rapid advancements in space-based telescopes and detection techniques. But the mere discovery of a planet beyond our solar system is only the beginning to understand whether these alien worlds harbor the potential for life. We must peer beyond their orbits and masses. We must examine their atmospheres. And to do so, we follow the trails of heat, thermal signatures that tell us about their chemistry, their climates, and their capacity to nurture life. An exoplanet's atmosphere acts as a thermal lens, filtering starlight, absorbing radiation, and re-emitting energy in ways that can be measured across the electromagnetic spectrum. Unlike the rocky surface of a planet or its dense interior, an atmosphere is dynamic, ever-shifting, with wind, weather, and heat transport, and it is through these subtle changes in emitted thermal energy that we learn what kind of molecules float within these veils of gas, whether water vapor, carbon dioxide, methane, or oxygen, and how they interact with incoming stellar radiation. The process of detecting atmospheric composition begins with a technique known as transit spectroscopy. When an exoplanet passes in front of its host star, a portion of starlight filters through the planet's atmosphere before reaching our telescopes. That light carries with it a distinct fingerprint, specific wavelengths absorbed or scattered by gases like ammonia, hydrogen, or ozone. But more than just composition, the temperature of these atmospheres can be inferred based on the intensity and distribution of infrared radiation, especially during the planet's secondary eclipse, when it passes behind its star and its thermal signature briefly vanishes. By comparing the light before and after this eclipse, astronomers can measure how much infrared energy the planet was emitting, revealing its dayside temperature, heat redistribution patterns, and even weather systems. Hot Jupiters, gas giants that orbit close to their stars, have been a fertile ground for such thermal studies. These massive planets, often scorched by stellar proximity, can reach thousands of degrees in temperature. Their atmospheres are turbulent and chaotic, with winds whipping across their skies at thousands of miles per hour. In some, astronomers have detected temperature inversions, where the upper atmosphere is hotter than the layers beneath, caused by high-altitude absorbers such as titanium oxide. These thermal inversions alter the expected spectral lines and provide clues to atmospheric layering and circulation. But thermal signatures also help us distinguish more temperate exoplanets, rocky Earth-like bodies that orbit within the habitable zones of their stars. Planets like those in the TRAPPIST-1 system or those orbiting red dwarfs, while smaller and cooler, offer tantalizing hints of atmospheric retention and heat balance. By carefully modeling the thermal emission from such planets, scientists can estimate greenhouse gas concentrations, surface pressure, and albedo, the reflectivity of a planet's surface or cloud layers. These factors, in turn, help refine our understanding of whether the planet might maintain liquid water on its surface, a prerequisite for life as we know it. Atmospheric escape, another thermally driven phenomenon, is crucial in shaping the evolution of exoplanetary environments. On planets with low gravity or weak magnetic fields, high-energy ultraviolet and X-ray radiation from their stars can heat the upper atmosphere, giving particles enough energy to escape into space. This process, known as hydrodynamic escape, has stripped many smaller exoplanets of their primordial hydrogen envelopes, leaving behind bare rocky cores or reshaped composition. By studying thermal emissions in ultraviolet and X-ray wavelengths, researchers can track this atmospheric loss in real time, witnessing how stellar radiation sculpts planetary fates. The James Webb Space Telescope has ushered in a new era of thermal detection, pushing the boundaries of what we can measure. With its unmatched infrared sensitivity, it has begun detecting faint heat signatures from temperate exoplanets, hinting at surface pressures, possible volcanic activity, and even seasonal variations. Observations of carbon dioxide absorption in the atmosphere of exoplanet WASP-39b, for example, confirmed not only its thermal structure, but also offered evidence of atmospheric mixing and photochemical reactions. These insights provide vital context for understanding planetary development in diverse environments. Exoplanetary thermal signatures are not just passive reflections of radiation, they are fingerprints of planetary identity, revealing a planet's history, its climate engine, and the delicate balance that governs habitability. For instance, tidal heating, a form of internal thermal energy generated by gravitational interactions, can drive volcanic activity and alter the thermal output of exomoons or planets in eccentric orbit. Such internally driven heat sources may allow subsurface oceans to exist on worlds otherwise too distant from their stars for surface water, challenging the traditional view of the habitable zone. In parallel, atmospheric chemistry influenced by thermal dynamics opens doors to biosignature detection, the coexistence of gases like methane and oxygen, which react rapidly in most environments, could signal biological replenishment if found together. But these gases behave differently under varying thermal profiles, requiring precise modeling of temperature gradients and geological transfer to distinguish biological origins from geological or photochemical sources. The field is still in its infancy. Yet with each exoplanet surveyed, with each thermal spectrum captured, we inch closer to answering one of humanity's oldest questions. Are we alone? The thermal whispers from alien skies, barely perceptible across light years, carry with them the secrets of distant climates, lost oceans, evolving atmospheres, and perhaps even alien biology. As we follow the trail of heat outward, from the familiar to the alien, we are reminded that temperature is more than a physical property. It is a storyteller, encoding the past, present, and future of distant worlds. It gives shape to atmospheres, fuels weather, drives chemistry, and defines the fragile conditions under which life might emerge. And just as the delicate dance of atmospheric temperature shapes the fate of exoplanets, the interplay of temperature and gravity within stellar cores sets the stage for the next chapter. From the layered envelopes of gas giants and terrestrial bodies, we now dive deeper into the hearts of stars, where intense gravitational compression gives birth to stellar ignition. In the next outline, we journey into the furnace of nuclear fusion, exploring how heat and pressure combine to transform hydrogen into helium and release the energy that powers the stars. In the cold, dark vastness of interstellar space, where starlight barely reaches and temperatures drop to just a few degrees above absolute zero, there exists a realm of cosmic chemistry so delicate and yet so vital to the evolution of the galaxy that its significance is only beginning to be understood. It is here, in the frigid hearts of dense molecular clouds, that interstellar ices quietly coat tiny dust grains, acting as laboratories for physical transformations that ultimately seed the birth of stars, planets, and perhaps even life itself. Though visually invisible, these microscopic ice mantles bear witness to a continuous dance between energy and matter. Through heating, sublimation, refreezing, and chemical evolution that forms one of the most intricate and fundamental processes in the interstellar medium. Interstellar ices are primarily composed of simple molecules: water, carbon dioxide, carbon monoxide, ammonia, methane, and methanol among them. These substances form when atoms and molecules condense onto dust particles in extremely cold environments where temperatures fall below 50 Kelvin. Under such chilling conditions, hydrogen and oxygen atoms settle on the surfaces of silicate or carbonaceous dust grains, forming water ice through a process known as surface catalysis. Similar processes produce other volatiles, leading to complex multi-layered ice structures that evolve chemically and physically over time. These ices remain dormant, sometimes for millions of years, preserved in the cold shadows of molecular clouds, until they are stirred by the arrival of heat. The introduction of heat in these frozen realms is not random. As gravitational forces begin to collapse dense regions of a molecular cloud into protostars, temperatures begin to rise. The collapse of a cloud core into a luminous young stellar object sends waves of radiation into the surrounding environment, warming the dust and ice. As temperatures climb past 100 Kelvin, phase transitions begin. The ices, once stable in solid form, start to sublimate directly into gas, bypassing the liquid phase due to the low pressure of space. This process, known as thermal desorption, releases a cascade of molecules into the surrounding medium, drastically altering the chemistry of the nascent star-forming region. These liberated molecules include not only the original components of the ices, but also more complex organics, synthesized within the ice itself over cosmic timescales. Laboratory studies and telescope observations, particularly from infrared instruments like the James Webb Space Telescope and its predecessors, have revealed the signatures of these sublimating ices. When heated, water ice shows sharp vibrational features in the infrared, while carbon monoxide and methane produce distinctive absorption bands that allow astronomers to trace their presence across interstellar regions. The detection of these spectral fingerprints not only maps the distribution of ices in protostellar environments, but also provides clues about their temperature history, molecular composition, and exposure to ultraviolet radiation. In regions where young stars emit intense radiation or shockwaves propagate through the cloud, the ices undergo photodesorption, where high-energy photons break chemical bonds and release atoms and radicals from the ice into the gas phase, further fueling astrochemical reactions. What emerges from these thermal events is far more than a temporary disturbance. The chemical evolution initiated by phase changes in interstellar ices becomes the foundation for the organic richness of planetary systems. As icy grains are incorporated into protoplanetary disks, the molecules they carry are delivered to growing planets and comets. It is believed that Earth's own water and a substantial portion of its prebiotic organic material arrived via such icy messengers. In this sense, interstellar ice is not merely a passive component of the cosmic landscape, but a carrier of complexity, one that bridges the cold simplicity of the interstellar medium with the intricate chemistry of life. Furthermore, the role of heat in triggering these transformations is multifaceted. It is not limited to thermal energy from stars, but also includes shocks from supernova explosions, turbulence within molecular clouds, and even interactions with cosmic rays and high-energy particles. Each of these heat sources can induce specific phase changes and chemical pathways. For instance, cosmic rays can penetrate deep into dense clouds, depositing energy that allows radical chemistry to proceed even in shielded environments. As a result, interstellar ices exposed to a combination of low-level heat and radiation may host a kind of prebiotic chemistry that mimics the conditions of early Earth, long before planetary systems are even fully formed. In the broader galactic context, the phase behavior of ices also helps regulate the thermal balance of the interstellar medium. Sublimating ices release latent heat, warming nearby regions and altering local gas dynamics. At the same time, the deposition of ices on dust grains contributes to cooling by allowing infrared radiation to escape more efficiently. These processes influence cloud fragmentation, star formation efficiency, and the structure of molecular clouds on galactic scales. The delicate interplay between heating and cooling, freezing and sublimation, reveals that even the quietest corners of the universe are in a constant state of dynamic thermal evolution. The study of these icy transformations is still expanding. As observational tools grow more powerful and laboratory simulations become more precise, scientists are uncovering new molecular species hidden within the ice, including complex organics that hint at the seeds of biology. The boundary between chemistry and astrophysics continues to blur, offering a view of the cosmos not just as a physical mechanism, but as a thermally driven alchemical cauldron, where elements and energies converge. And so, from the invisible frost clinging to interstellar grains, we find a story of thermal metamorphosis. An account of how cold, quiet matter awakens under heat's influence and evolves into a source of chemical diversity across the galaxy. As these ices continue their transformation journey, they eventually become incorporated into larger celestial bodies and even star systems, thereby influencing the thermal behavior of entire galactic environments. As we now shift our gaze outward once more, toward the largest gravitationally bound systems in the universe, we arrive at the next frontier in our thermal odyssey, the velocity fields and temperature flows of expanding galaxy clusters. In these colossal arenas, heat and motion are not confined to tiny grains of ice, but span millions of light years, sculpting the dynamics of cosmic structure on the grandest scale. The role of temperature in shaping planetary habitability. In the vast and varied theatre of the cosmos, temperature plays one of the most decisive roles in determining whether a planet is merely a desolate orb or a potential cradle for life. More than distance from a star, more than the presence of water, or even atmospheric composition, temperature dictates the underlying physics and chemistry that drive habitability. It is the thread that weaves together climate stability, chemical reactivity, atmospheric dynamics, and biological processes. And it is this variable, this seemingly simple metric of thermal energy, that has influenced the course of habitability from Earth to the most distant exoplanets known today. The story of temperature and habitability begins with the fundamental principle of the habitable zone, often referred to as the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on a planet's surface. This region around a star defines a rough corridor where thermal conditions allow for water to remain in its liquid phase, a condition most biologists agree is essential for life as we know it. But the habitable zone is not a fixed distance. Its boundaries shift based on the luminosity and age of the host star. For young, cooler stars like red dwarfs, the zone lies much closer. For massive, short-lived stars like blue giants, it drifts far out, though usually without remaining stable long enough for life to emerge. Even within this zone, temperature is not dictated solely by a planet's proximity to its star. Atmospheric composition plays a crucial role. The greenhouse effect, particularly the presence of gases such as carbon dioxide, methane, and water vapor, traps heat and moderates the surface temperature. On Earth, this natural process has maintained a stable climate for billions of years, allowing life to flourish. Yet, on Venus, a runaway greenhouse effect has turned a once potentially habitable world into an inferno, where surface temperatures soar high enough to melt lead. Conversely, on Mars, the thin atmosphere fails to retain sufficient heat, plunging it into a frigid wasteland despite being within the Sun's habitable zone. Temperature also regulates the chemical pathways that underpin prebiotic chemistry. Organic molecules necessary for life are sensitive to heat. Too cold and chemical reactions are sluggish or cease. Too hot and complex molecules break apart. On early Earth, hydrothermal vents and warm, shallow seas may have provided the ideal thermal gradient to catalyze the formation of amino acids, nucleotides, and other organic precursors. Thus, habitability is not merely about sustaining life, but also about creating it. And temperature sits at the core of both processes. Beyond chemistry, temperature gradients help drive planetary weather and ocean currents, redistributing heat across the globe and moderating extremes. On Earth, these patterns give rise to temperate climates and biomes. Planets without significant axial tilt, or with tidally locked rotations where one side perpetually faces the star, suffer from thermal imbalance, with scorching daylight sides and frozen night sides, conditions that challenge habitability unless mechanisms such as thick atmospheres or subsurface oceans moderate the heat. The presence of plate tectonics, volcanism, and magnetic fields, all influenced by a planet's internal heat, further affect climate stability, atmospheric replenishment, and protection from harmful stellar radiation. The thermal history of a planet is equally critical. Earth has seen dramatic shifts in temperature over geologic time: snowball Earth episodes, greenhouse periods, and ice ages. These fluctuations have influenced evolutionary pathways, acted as selective pressures, and even reset the biosphere multiple times. Habitability, therefore, is not static. It evolves, shaped by internal and external factors, many of them rooted in thermal dynamics. So for exoplanets, measuring temperature profiles offers a window into their potential to harbor life. Using techniques like transit spectroscopy and infrared emission analysis, astronomers can estimate atmospheric temperatures and even identify possible greenhouse gases on planets such as TRAPPIST-1e or Kepler 442b. Thermal signatures hint at conditions that might permit liquid water, but temperature must always be interpreted in the broader context of atmospheric pressure, composition, stellar activity, and geological processes. Temperature also shapes the longevity of habitability. A planet may only remain within the habitable zone for a limited window of time. Stars like our Sun brighten as they age, moving the habitable zone outward. Eventually, Earth will grow too hot to sustain life. Thus, for long-term habitability, a planet must either adapt or relocate. A notion that pushes the boundary of habitability from planetary physics into speculative astrophysics and interstellar engineering. Recent discoveries of subsurface oceans on moons like Europa and Enceladus further complicate the picture. These environments may harbor life beneath thick, icy shells, heated not by sunlight but by tidal friction and radioactive decay. Here, temperature no longer depends on distance from the Sun, but on internal energy, opening up a new class of potentially habitable worlds. Warm in the dark, alien yet promising. In essence, temperature is both gatekeeper and sculptor of planetary habitability. It decides not just if life can exist, but how it forms, evolves, and endures. As scientists peer deeper into the cosmos, characterizing the thermal environment of distant planets will remain a cornerstone of astrobiology, guiding the search for worlds like or unlike our own. And as we contemplate the subtle, complex interplay between thermal energy and biological potential, we are naturally led into the next arena of cosmic inquiry, where the very heat that nourishes life can also transform it, vaporize it, or preserve it in icy stillness for eons. It is within this paradox that we find our next question waiting. How do interstellar ices respond to the silent caress of heat? In the immense and ancient theatre of the cosmos, where stars collapse and galaxies collide, where heat and light define the birth and death of entire worlds, there exists a subtle yet profound force, the thermal gradient, a quiet architect in the vast blueprint of life's potential across the universe. From the cores of stars to the frigid boundaries of interstellar voids, temperature is not merely a measure of energy. It is a language spoken by atoms and molecules, a code etched into the very scaffolding of matter and time. And in this closing arc of our cosmic journey, we confront one of the most urgent and philosophical questions ever asked by our species. Where might life exist beyond Earth? And how does the universe's thermal structure guide that search? A thermal gradient is the variation of temperature across space, a shift from hotter to colder regions, whether over millimeters in a hydrothermal vent or across light years between stars. It is not a minor detail in planetary science or astrobiology. Rather, it is the essential condition for dynamic processes. Life, as we understand it, does not thrive in thermal equilibrium. It thrives in gradients, in the flows and exchanges of energy between warm and cold, between active and inert, between chaos and order. On Earth, this principle is foundational. Life began in places where temperature differences sparked chemical interactions, possibly near hydrothermal vents at the ocean floor, where hot, mineral-rich water met icy seawater, generating complex chemistry that would seed biological evolution. These same rules apply when we extend our gaze beyond our planet. Planets and moons do not merely need liquid water, stable atmospheres or magnetic shields. They need energy flows, and those flows are regulated by temperature differences. The more stable and long-lasting the gradient, the more likely it is to sustain biological complex. Moons such as Europa and Enceladus, buried beneath sheets of ice but believed to harbor subsurface oceans, draw attention not just for their water, but for the suspected heat emanating from their cores, creating gradients that could mimic Earth's deep-sea ecosystems. Similarly, exoplanets orbiting in the so-called Goldilocks zone, not just at the right distance from their stars, they also must support internal or atmospheric temperature differentials that allow for convection, weather, and ultimately, life-supporting chemical reactions. But understanding the role of thermal gradients in astrobiology requires deep dives into astrophysics, chemistry, and planetary geology. Stars radiate energy across a spectrum, and the absorption and distribution of this energy on orbiting bodies depends on a planet's atmosphere, rotation, tilt, and geological activity. A planet locked tidally, always showing the same face to its star, might still harbor life if the thermal gradient between its blistering dayside and frozen nightside drives powerful winds or ocean currents. In contrast, a world bathed in even heat, with no contrast, might stagnate in biological potential. Even more exotic are rogue planets, free-floating worlds not tethered to any star. At first glance they seem too cold and dark to support life, but if these worlds possess radioactive cores or ancient geothermal remnants, then gradients could form between a warm interior and a frozen surface, creating micro-environments that defy expectation. Life in such places would be stranger than fiction. Alien not only in biology, but in its thermal reality. The story of thermal gradients also intersects with our study of atmospheres and greenhouse effects. On Earth, the atmosphere traps solar energy, redistributes it, and maintains a gradient from equator to pole, driving wind, rain and climate. On Venus, a runaway greenhouse effect erases most gradients, creating a planet where temperature is nearly uniform and uniformly hostile. On Mars, a thin atmosphere means dramatic fluctuations between sunlit and shaded areas, making thermal gradients too extreme for liquid water to persist on the surface. These examples show how finely tuned the thermal environment must be. Not just warm, but layered, dynamic, and sustained. As we peer deeper into the galaxy with telescopes like the James Webb and the next generation of observatories, we are not only looking for blue dots and Earth twins, we are looking for thermal clues, subtle fingerprints of gradients in atmospheric composition, infrared emissions, seasonal temperature shifts, and albedo changes that might betray internal heat sources or volatile cycles. These gradients are not just background information. They are the evidence trail left by planetary engines, possibly at work, mixing elements and giving rise to complexity. Temperature also shapes chemistry. In environments that are too cold, reactions happen slowly or not at all. In places too hot, molecules disintegrate before they can combine into anything useful. But in the right thermal window, at the right gradient, carbon can bond with hydrogen, oxygen with nitrogen, and organic molecules can evolve into biochemistry. It is here, in these thermally moderate zones, with active differentials, that the seeds of life may sprout. Just as mitochondria in Earth's cells use a proton gradient to produce energy, life elsewhere might rely on similar thermal mechanisms, adapted to alien chemistries and unknown solvents. Even theoretical life on gas giants or exotic worlds might be driven by gradients, not necessarily of temperature alone, but of entropy, radiation, or magnetic energy, all of which ultimately tie back to thermal dynamics. In this sense, our understanding of thermal gradients is not a narrow inquiry, but a wide-angle lens on the nature of complexity in the universe. And so, as we close this journey across black-body radiation and stellar temperatures, across dying white dwarfs and gas giant storms, across icy moons and faraway exoplanets, we arrive at a simple but profound insight. The search for life is, at its core, a search for gradients. Life is not an isolated miracle. It is a thermodynamic phenomenon, a pattern that arises when energy is allowed to flow, when systems are out of balance, just enough to evolve, adapt, and remember. We have followed the trail of heat from the hearts of stars to the coldest edges of interstellar space, and now we see that thermal gradients are not just clues to life's existence, they are the very preconditions of life's emergence. The cosmos does not merely tolerate life. Under the right conditions of temperature and energy flow, it appears to encourage it. In the end, as we return our gaze from the infinite to the intimate, from galaxies to grains of interstellar dust, we realize that the forces shaping our universe, gravity, radiation, magnetism, and above all heat, are not just indifferent engines of physics. They are the sculptors of possibility. And in their hands, guided by the subtle dance of temperature gradients, life may yet emerge again and again, scattered like seeds in a soil of stars, waiting only for the right fire and the right cold to awaken. In the vast, ever-expanding frontier of human exploration, there exists a journey so awe-inspiring and monumental that it transcends the very boundaries of time and space. This epic voyage is none other than the extraordinary odyssey of Voyager 1, a pioneering spacecraft launched by NASA that has traveled farther than any other human-made object, carrying the hopes and dreams of humanity into the deepest reaches of the cosmos. Recently, Voyager 1 sent back a historic transmission to Earth that has ignited waves of excitement and curiosity throughout the global scientific community and beyond. At the heart of this remarkable message lies a discovery of unparalleled significance, an enigmatic object detected in the profound, uncharted depths of interstellar space. This mysterious revelation has reignited one of the most timeless and compelling questions that has captivated humanity for generations. Could this signal represent the long-awaited moment when we finally establish contact with advanced extraterrestrial life? For centuries, humankind has gazed up at the night sky with wonder, imagining the possibility of other civilizations thriving among the stars. Now, this revelation has brought those age-old dreams tantalizingly close to reality. Voyager 1's journey began decades ago when it was launched on September 5, 1977, as part of NASA's ambitious Voyager program. Its mission was bold and profound: to act as Earth's emissary, venturing beyond the familiar realms of our solar system into the vast unknown, while meticulously studying the outer planets and their moons. Voyager 1's remarkable voyage was marked by a serendipitous cosmic alignment. It set off just 16 days before its twin, Voyager 2, beginning a cosmic ballet that has unfolded for more than 40 years. What truly sets Voyager 1 apart from countless other space missions is its extraordinary spirit of communication. Despite its unfathomable distance from Earth, Voyager 1 maintains a steadfast dialogue with our home planet through NASA's venerable deep space network. This complex and powerful communication system allows Voyager 1 not only to receive commands, but also to transmit back invaluable streams of scientific data, bringing us ever closer to understanding the cosmos. As of the latest measurements, Voyager 1 is an astonishing 159.32 astronomical units AU away from Earth, equivalent to nearly 23.8 billion kilometers, or approximately 14.8 billion miles. This staggering distance makes it the most distant human-made object ever to voyage into space. Yet, despite this incredible remoteness, Voyager 1's instruments continue to operate, tirelessly collecting and sending back information that deepens our understanding of the universe around us. Voyager 1's primary mission was to explore the outer boundaries of the heliosphere, the vast bubble of charged particles and magnetic fields generated by the Sun. This outer boundary, called the heliopause, marks the frontier where the influence of our star gives way to the cosmic environment of interstellar space. Crossing this threshold in 2012, Voyager 1 became the first human-made object to enter the space between stars, beginning a new chapter in space exploration. What makes Voyager 1's mission truly remarkable is not only its groundbreaking discoveries, but also its extraordinary endurance. Originally designed to last only a few years, Voyager 1 has surpassed all expectations, continuing its interstellar journey for over 4 decades. Each day, it cruises through the void at an incredible speed of approximately 38,000 miles per hour, sending precious data back to Earth across billions of miles. Scientists anticipate that Voyager 1 will continue this historic mission at least until 2025, when its power sources are expected to diminish. Equipped with a sophisticated suite of 10 scientific instruments, including cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, cosmic ray sensors, and radio science equipment, Voyager 1 was built to be humanity's eyes and ears in the cosmos. These instruments have enabled the spacecraft to withstand the harsh and unforgiving conditions of deep space, while delivering an unprecedented wealth of knowledge about the outer solar system and beyond. Among Voyager 1's most celebrated achievements are its close flybys of two colossal gas giants, Jupiter and Saturn. In 1979, Voyager 1 made its first close approach to Jupiter, revealing breathtaking details about the planet's turbulent atmosphere, intricate ring system, and diverse moons. The spacecraft's instruments confirmed the existence of faint rings around Jupiter, previously only theorized, and uncovered previously unknown moons that added to our understanding of the planet's complex environment. A year later, in 1980, Voyager 1's encounter with Saturn provided equally stunning insights. It unveiled the intricate structure of Saturn's iconic rings, captured detailed images of its moons, and deepened our knowledge of the planet's magnetic field and atmosphere. These flybys not only revolutionized planetary science, but also inspired a new generation of explorers, scientists, and dreamers around the world. One of the most iconic moments in Voyager 1's journey came in 1990, when the spacecraft, prompted by the visionary astronomer Carl Sagan, turned its cameras back toward Earth and captured the now famous image known as the pale blue dot. In this extraordinary photograph, Earth appears as a tiny speck suspended in a vast cosmic ocean, a fragile and precious home floating in the immense void of space. This image remains a powerful symbol of humanity's shared vulnerability and interconnectedness, reminding us of the urgent need to cherish and protect our only home. As Voyager 1 continues its silent journey through the darkness beyond our solar system, it carries with it the legacy of human curiosity, ingenuity, and the unquenchable desire to explore. Its latest discovery in the depths of interstellar space hints at new cosmic mysteries waiting to be unveiled, perhaps even the momentous encounter with other life forms that so many have dreamed about. This odyssey, which began over 4 decades ago, continues to inspire and challenge us, inviting us all to look up, wonder, and reach ever further into the vast expanse of the universe. Voyager 1 was designed to push the boundaries of human knowledge, traversing vast distances where no spacecraft had dared to go before. Equipped with a suite of sophisticated scientific instruments, it was tasked with studying the giant planets and their moons, capturing unprecedented data that would forever change our understanding of the solar system. What makes Voyager 1 truly extraordinary is not just its groundbreaking discoveries, but its resilience and longevity. Despite being launched over 4 decades ago, it continues to send invaluable information back to Earth, maintaining a lifeline of communication through NASA's Deep Space Network. This unwavering connection allows scientists to receive data from more than 14 billion miles away, a testament to human ingenuity and determination. As Voyager 1 journeys beyond the heliosphere, the protective bubble created by the sun's solar wind, it enters interstellar space, a vast expanse filled with cosmic mysteries. Recently, a signal from Voyager 1 revealed the detection of an enigmatic object lurking in this farthest frontier. This revelation has sent shockwaves through the scientific community and reignited a question that has fascinated humanity for generations. Are we alone in the universe? The possibility that this mysterious detection could be evidence of advanced extraterrestrial life has captivated imaginations worldwide, inspiring scientists, philosophers, and dreamers alike to ponder the cosmic significance of this discovery. As we delve deeper into Voyager 1's findings, we are reminded of the boundless curiosity that drives human exploration, our relentless quest to understand not only the universe, but our place within it. In this unfolding cosmic saga, Voyager 1 stands as a symbol of hope, perseverance, and the unquenchable thirst for knowledge. Its voyage is not merely a scientific endeavour, but a profound journey that connects us all, uniting humanity in awe of the infinite cosmos that stretches beyond our wildest dreams. An intriguing aspect of the Voyager mission narrative lies in the remarkable timing. Voyager 1 began its epic journey just 16 days ahead of its cosmic twin, Voyager 2. This serendipitous alignment lends a sense of cosmic symmetry to an unparalleled saga. Two intrepid emissaries of humanity, launched in close succession, each destined to explore the uncharted realms of our solar system and beyond. What truly distinguishes Voyager 1 from countless other space missions is its indomitable spirit of communication, a lifeline that it maintains steadfastly with Earth across unimaginable distances. This extraordinary feat is made possible by NASA's venerable Deep Space Network, a robust and sophisticated communication infrastructure designed to ensure a constant dialogue between the spacecraft and its home planet. This unyielding link serves a dual purpose. It allows Voyager 1 to receive precise commands from mission control and, in return, to transmit a treasure trove of invaluable scientific data back to its terrestrial origins. According to the most recent data, Voyager 1 currently finds itself at an astonishing distance of approximately 159.32 astronomical units (AU) from Earth. To put this monumental achievement into perspective, this distance translates to an awe-inspiring 23.834 billion kilometers, or roughly 14.8 billion miles, away from the cradle of humanity. In other words, Voyager 1 is now the most distant human-made object in existence, a lone traveler venturing farther into the cosmic ocean than any other craft before it. This staggering remoteness not only speaks to the spacecraft's incredible durability and the brilliance of human engineering, but also marks a milestone in our quest to understand the universe around us. It is this incomprehensible remoteness that firmly establishes Voyager 1 as the most distant human-made object ever to embark on an odyssey into the vast cosmos. From the moment of its launch, Voyager 1's primary mission objective was clear and profoundly ambitious: to explore and meticulously scrutinize the boundaries of the outer heliosphere, a mysterious and barely understood region known as the heliopause. This invisible boundary marks the outermost layer of the Sun's influence, the final frontier where the solar wind meets the vast interstellar medium, enveloping our entire solar system in a protective bubble. Through its relentless investigations, Voyager 1 has bestowed humanity with invaluable insights into the cosmos, especially within the confines of our immediate solar neighborhood. Propelled forward at an astonishing velocity of approximately 38,000 miles per hour, an incredible speed that allows it to traverse vast cosmic expanses day by day, the spacecraft continues to push the boundaries of exploration and knowledge. Yet, what truly sets Voyager 1 apart is not just its distance or speed, but its remarkable endurance. The spacecraft has not merely met expectations, it has far exceeded its originally projected lifespan. More than 4 decades after its historic launch, Voyager 1 remains operational, tirelessly sending back vital data from the farthest reaches of space. Its ongoing mission serves as a testament to human ingenuity, perseverance, and an insatiable desire to understand the universe around us. Voyager 1 has embarked on extraordinary decades of exploration, defying the limits of time and technology. Each passing day, this remarkable spacecraft dutifully records and transmits vital information about its celestial journey, offering humanity a continuous stream of priceless data from the edge of our solar system and beyond. Remarkably, Voyager 1 is expected to continue this awe-inspiring interstellar sojourn until at least the year 2025, a testament to its resilient propulsion systems and enduring power supply that have kept it operational far beyond initial expectations. By that time, it is estimated that Voyager 1 will have achieved an almost inconceivable distance of approximately 13.8 billion miles from the nurturing embrace of the Sun, a staggering measure of its pioneering voyage into the cosmic unknown. Accompanying Voyager 1 on this grand adventure is its celestial sibling, Voyager 2, both launched as part of NASA's legendary Voyager program. Together, they were equipped with a formidable array of 10 unique scientific instruments, each serving as sensory extensions of the spacecraft into the vast cosmos. This sophisticated ensemble of tools included television cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, cosmic ray and charged particle sensors, as well as state-of-the-art radio equipment, all meticulously designed to conduct groundbreaking experiments. These ingenious instruments have endowed Voyager 1 with the resilience and capability to withstand the harsh and unforgiving environs of deep space, allowing it to probe the unfathomable reaches of the unknown. One of the most indelible milestones in Voyager 1's storied journey was its close encounters with two of the most majestic and enigmatic bodies in our solar system, Jupiter and Saturn. These historic flybys provided humanity with an unprecedented window into the complexities and wonders of these gas giants, forever reshaping our understanding of the planetary giants and their moons. Voyager 1's encounters with the solar system's colossal planets, Jupiter and Saturn, were nothing short of historic. These celestial rendezvous, which occurred in 1979 and 1980, respectively, marked a watershed moment in the annals of scientific discovery. Through these close flybys, Voyager 1 gifted humanity with an unprecedented glimpse into the intricate complexities of these gas giants and their enigmatic retinues of moons. The spacecraft etched its name indelibly into history by uncovering previously unknown moons orbiting these planets, and by revealing the intricate and delicate ring structures that encircled both Jupiter and Saturn. Prior to Voyager 1's mission, much of this was speculation or incomplete knowledge. Its groundbreaking revelations not only captivated the scientific community, but also ignited the imaginations of people across the globe, heralding a new era of planetary exploration. One of Voyager 1's most iconic and enduring contributions to our cosmic understanding came in 1990 when the celebrated astronomer Carl Sagan championed a visionary concept. He urged the spacecraft to pivot its cameras and direct its lens back towards Earth. This simple yet profound act resulted in the creation of the now famous image known as the pale blue dot. The resulting image, now deeply etched into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant image serves as a humbling reminder of the fragility and interconnectedness of our planet, underscoring the imperative to cherish and protect our world. A message that continues to resonate powerfully with people around the globe. Voyager 1's epic journey through the cosmos led it to encounter two of the most enigmatic and majestic celestial bodies in our solar system, Jupiter and Saturn. These monumental encounters provided a treasure trove of scientific data and imagery, fundamentally reshaping our understanding of these gas giants. Jupiter, the largest planet in our solar system, beckoned Voyager 1 with its beguiling mysteries. In March 1979, the spacecraft conducted a close flyby of this colossal giant, granting humanity its first intimate glimpse of the planet's immense scale and complexity. As Voyager 1 ventured closer, it unveiled a tapestry of astounding discoveries. One of the most captivating being the confirmation of Jupiter's intricate ring system. Before Voyager 1's arrival, these faint rings were only a hypothesis, but the spacecraft's keen instruments provided definitive evidence of their existence. Composed of fine, dark particles, these delicate rings encircle Jupiter in an ethereal fashion. The images captured by Voyager 1 offered an entrancing perspective on this subtle feature, captivating the world with their delicate beauty and adding a new dimension to our cosmic knowledge. Another remarkable revelation from Voyager 1's encounter with Jupiter was the unveiling of intricate weather patterns and tempestuous storms on the gas giant's surface. Among these tempests, the most iconic was the Great Red Spot, a colossal storm that has raged for centuries. Voyager 1's imagery of this mammoth tempest not only illuminated the storm's complex structure and dynamic behavior, but also ignited the public's fascination with Jupiter's tumultuous atmosphere. Furthermore, Voyager 1's instruments detected Jupiter's powerful magnetosphere, a colossal magnetic field that dwarfs Earth's own magnetic envelope. This groundbreaking discovery provided crucial insights into the planet's magnetic dynamo and shed light on how this immense magnetic field interacts with its retinue of moons, influencing their environments and contributing to the complex space weather around Jupiter. Following its momentous encounter with Jupiter, Voyager 1 continued its epic odyssey toward Saturn, the majestic ringed planet. In November 1980, the spacecraft made its closest approach to this cosmic wonder, offering humanity an intimate view of Saturn's stunning rings and captivating moons. The detailed images and data collected unveiled previously unseen features of the ring's delicate structure and composition, as well as the diverse geology and atmospheres of Saturn's many moons. One of Voyager 1's most iconic contributions to human perspective came in 1990 with the celebrated pale blue dot image. The esteemed astronomer Carl Sagan championed a visionary idea. He implored the spacecraft to pivot its cameras and turn its lens back toward Earth. This image immortalized our planet as a tiny, fragile speck suspended in the vastness of space, inspiring reflection on our place in the cosmos and a renewed commitment to safeguarding our shared home. The resulting image, now etched deeply into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant and humbling image serves as a powerful reminder of the fragility, vulnerability, and profound interconnectedness of our planet within the boundless expanse of the universe. It underscores the urgent imperative to cherish, protect, and preserve our delicate home, a message that continues to resonate with people from all corners of the globe, inspiring reflection on our shared responsibility to safeguard life on Earth. While Voyager 1's extraordinary odyssey primarily focused on the majestic gas giants Jupiter and Saturn, its twin spacecraft, Voyager 2, embarked on a distinct and equally remarkable trajectory. Voyager 2 was destined to explore the enigmatic ice giants of our solar system, Uranus and Neptune, planets shrouded in mystery and complexity, presenting a fresh array of cosmic enigmas for scientists and humanity to unravel. Uranus, the seventh planet from the Sun, is a celestial enigma for many reasons, not least of which is its extraordinary rotation. Unlike any other planet in our solar system, Uranus rotates on its side, with an axial tilt of approximately 98 degrees. This unusual orientation is believed to be the aftermath of a colossal and cataclysmic collision with a massive celestial object in the distant past, which drastically altered the planet's spin. This tilt results in extreme seasonal variations lasting over decades, offering a unique glimpse into planetary dynamics that differ greatly from those of Earth and its planetary neighbours. Despite its unusual tilt and mysterious origins, Uranus remains a captivating and fascinating world. It is approximately 4 times the diameter of Earth and boasts a cold, icy atmosphere composed mainly of hydrogen, helium and methane, giving it a characteristic blue-green hue. Voyager 2's historic flyby of Uranus in January 1986 marked a momentous milestone in space exploration. For the first time, humanity received detailed images and comprehensive scientific data of this distant ice giant, expanding our knowledge far beyond previous telescopic observations. Among the many groundbreaking discoveries during Voyager 2's encounter was the revelation that Uranus possesses a complex system of rings, a surprising finding since rings were once thought to be unique to Saturn. Voyager 2 revealed that these rings consist of dark, narrow bands composed of tiny particles and debris orbiting the planet, hinting at dynamic processes within Uranus's gravitational influence. In addition to its rings, Voyager 2 discovered 10 new moons orbiting Uranus, each with its own unique characteristics and geological histories. The spacecraft's instruments also provided valuable insights into the planet's atmosphere, uncovering high-speed winds and unexpected temperature variations that challenged existing models of planetary atmospheres. These findings offered a new window into the workings of ice giants, enriching our understanding of planetary formation and behavior in the outer solar system. Voyager 2's journey did not end with Uranus. It continued onward to Neptune, the outermost planet in our solar system, arriving in August 1989. Neptune, with its striking deep blue color and fierce weather systems, presented yet another frontier of exploration and discovery. The data and images sent back by Voyager 2 from Neptune's vicinity revealed powerful storms, supersonic winds, and a moon with active geysers. An astounding discovery that further deepened our appreciation for the dynamic complexity of these distant worlds. Together, the twin Voyager spacecraft have revolutionized our understanding of the solar system's outer realms. Their pioneering missions, spanning more than 4 decades, have transformed once faint and distant dots in the night sky into vividly detailed worlds, full of mystery and wonder. These missions continue to inspire generations of scientists, dreamers, and explorers, reminding us that even at the very edges of human reach, the universe holds countless secrets waiting to be discovered. Voyager 2 revealed a diverse and captivating retinue of moons orbiting Uranus, each possessing unique geological and atmospheric features. Among these, moons like Miranda, Ariel, and Titania stood out, showcasing dramatic landscapes marked by massive canyons, unusual fault lines, and evidence of past geologic activity. These discoveries significantly enriched humanity's understanding of Uranus, shedding light on the complex interactions between the planet and its satellites, and deepening the intrigue surrounding this enigmatic, sideways rotating giant. Voyager 2's interstellar voyage did not end at Uranus. It pressed onward, journeying even farther to reach Neptune, the 8th and most distant known planet from the Sun. Neptune, with its frigid temperatures and vibrant azure hue, remains a haunting symbol of the solar system's outer frontier. This distinct blue coloration is due to the high concentration of methane in its atmosphere, which absorbs red light and reflects the blue. In August 1989, Voyager 2 conducted a historic flyby of Neptune, marking the first, and so far only, close encounter with this distant world. The images and data transmitted back to Earth during this flyby were nothing short of revolutionary. Voyager 2 unveiled a planet with a surprisingly dynamic atmosphere, teeming with violent storms and fierce winds, the fastest sustained winds recorded in the solar system, reaching speeds of over 2,000 kilometers per hour, about 1,200 miles per hour. Among Neptune's most notable atmospheric features was the discovery of the Great Dark Spot, a colossal storm system reminiscent of Jupiter's famous Great Red Spot. However, unlike its Jovian counterpart, the Great Dark Spot proved to be ephemeral. It mysteriously vanished in later observations, raising questions about the atmospheric dynamics of Neptune and the transient nature of its weather system. Perhaps one of the most astonishing revelations from Voyager 2's Neptune encounter was the discovery of the planet's largest moon, Triton, to be an exceptional celestial body that defied expectations. Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction of Neptune's rotation. A rare trait that strongly suggests Triton is a captured object, possibly a former Kuiper Belt object that was gravitationally ensnared by Neptune in the distant past. Triton's surface was revealed to be a frozen yet geologically active world, exhibiting nitrogen geysers erupting from beneath its icy crust, a phenomenon never before observed on a celestial body so distant from the Sun. This cryovolcanic activity indicated that Triton, despite its remoteness and frigid temperatures, harbors internal heat and dynamic processes beneath its surface. Voyager 2's images showed a landscape marked by frozen plains, ridges, and sparsely cratered terrain, suggesting a young and possibly evolving surface. These groundbreaking discoveries at Neptune and Triton not only captivated the global scientific community, but also sparked the imaginations of people around the world. The Voyager 2 mission demonstrated the boundless potential of human curiosity and ingenuity, reminding us that even the most remote and mysterious corners of our solar system can be brought into the realm of human understanding. Voyager 2's historic flybys of Uranus and Neptune marked the end of humanity's first grand tour of the outer planets. A monumental chapter in the annals of space exploration, yet, like its twin Voyager 1, Voyager 2 continues to voyage beyond the known, transmitting faint whispers of data from the edge of interstellar space, ensuring that its legacy endures not just in scientific discovery, but in the shared human spirit of exploration. Triton, the largest moon of Neptune, emerged as one of the most fascinating and enigmatic celestial bodies encountered during Voyager 2's interplanetary odyssey. The spacecraft's imagery revealed a world brimming with activity, despite its remote location and frigid climate. Among Triton's most extraordinary features were geysers that erupted from beneath its icy surface, spewing nitrogen gas high into the moon's thin atmosphere. These geysers created vast plumes that extended kilometers above the surface, where the nitrogen would condense into snow-like particles and gently settle back to the ground, sculpting a surreal and alien landscape of frost and ice. This striking phenomenon was unlike anything previously observed in the solar system. offering profound insights into cryovolcanism, the eruption of volatile substances like water, ammonia or methane, rather than molten rock. Triton's surface, relatively young and sparsely cratered, hinted at a geologically active history, defying expectations for a moon so far from the Sun. Perhaps even more puzzling was Triton's retrograde orbit. It revolves around Neptune in the direction opposite to the planet's rotation. This uncommon trait strongly suggests that Triton did not form alongside Neptune, but was instead a captured object, likely originating from the Kuiper belt. Its gravitational capture would have disrupted Neptune's original satellite system and left Triton locked in a stable but unusual orbital dance, one that continues to intrigue astronomers to this day. Voyager 2's encounters with Uranus and Neptune remain unparalleled achievements in the history of space exploration. To this day, no other spacecraft has visited these distant ice giants, making Voyager 2's observations and data collection an irreplaceable scientific treasure. The trove of information gathered during these historic flybys continues to fuel research and hypotheses, offering glimpses into the atmospheric dynamics, magnetic fields, ring systems, and unique satellite compositions of these mysterious worlds. While Voyager 2 was delving into the secrets of the outer planets, its twin, Voyager 1, was forging an even more audacious path, a journey that would take it beyond the boundaries of the solar system and into interstellar space. This transition, which occurred in August 2012, marked a profound and historic milestone for humanity. For the first time, a human-made object had crossed the heliopause, the boundary where the solar wind yields to the interstellar medium. Voyager 1's entry into interstellar space did not signify the end of its mission, but rather the beginning of a new chapter. As it continues its voyage through the vast and silent reaches of the cosmos, it carries with it not only scientific instruments, but also a symbolic message from Earth, etched in the form of the Golden Record, a phonograph disc containing sounds, music, and greetings from our planet. Now billions of miles from Earth, Voyager 1 operates in a realm beyond the Sun's influence, where the environment is dominated by particles, fields, and forces that originate from other stars. Its instruments, though fewer in number now, continue to return invaluable data about the nature of interstellar space, helping scientists to understand the shape and boundary of the heliosphere and the conditions in the space between the stars. The enduring journey of the Voyager spacecraft, Voyager 1, venturing outward into the galaxy, and Voyager 2, providing the only close-up views of Uranus and Neptune, remains one of the most ambitious and successful missions in the history of space science. They have not only expanded the boundaries of human knowledge, but have also inspired generations to look upward and dream of what lies beyond, gathered groundbreaking data that challenged earlier assumptions and reshaped our understanding of this mysterious frontier. Rather than a simple comet-like structure with a long tail trailing away from the Sun, Voyager 1's measurements suggested that the heliopause is more complex, possibly a distorted bubble-like shape, influenced by both the solar wind from within and interstellar forces from beyond. As Voyager 1 crossed this boundary in 2012, it recorded a sudden and lasting drop in solar particles, while simultaneously detecting a surge in galactic cosmic rays, energetic particles that originate from supernovae and other powerful cosmic phenomena far outside our solar system. This was the smoking gun, clear empirical evidence that the spacecraft had exited the heliosphere and entered the vast ocean of interstellar space. Within this realm, Voyager 1's instruments continued to function, albeit in a limited capacity due to the fading power supply and increasing distance. Even so, its plasma wave subsystem detected a persistent background hum, long, low-frequency vibrations in the plasma of interstellar space. This discovery provided an unprecedented glimpse into the density and behavior of particles between the stars, and demonstrated that the void of space is, in fact, filled with subtle and dynamic forces. Voyager 1's ongoing mission in interstellar space is a testament to both technological resilience and scientific ambition. It represents the first time humans have been able to directly measure the environment of interstellar space, rather than relying solely on telescopes or theoretical models. The data sent back by Voyager 1 continues to challenge assumptions and refine our models of how the Sun interacts with the galaxy around it. As it sails farther into the unknown, Voyager 1 is also pushing the limits of communication. Its faint signals traveling at the speed of light now take over 22 hours to reach Earth. Each byte of data is a time capsule, whispering stories from the edge of the solar system to a waiting world. Despite being over 46 years old, the spacecraft continues to surprise. In recent years, engineers have performed innovative workarounds to keep it operational, including rerouting functions through backup systems. These efforts ensure that even in its twilight years, Voyager 1 remains a pioneer, a silent emissary of Earth, drifting among the stars. Its journey into interstellar space is not just a scientific achievement, but a symbolic one. Voyager 1 carries the golden record, a carefully curated message intended for any intelligent life that might one day encounter it. Engraved with greetings in 55 languages, music from cultures across the Earth, and images depicting life on our planet, the golden record serves as humanity's cosmic calling card, a whisper to the universe saying, "We were here, we reached this far, and we are curious." Voyager 1 is now far beyond the planets, beyond the influence of our star, continuing its voyage in the silence of deep space. It is alone, yet never forgotten. His legacy etched into history, its mission ongoing, and its story inspiring countless new explorers to reach for the stars. These observations from Voyager 1 provided a transformative understanding of the heliopause and its complex relationship with the galactic environment. Prior to Voyager's journey, much of what scientists knew about the heliosphere was theoretical, based on models, simulations, and indirect evidence. But as Voyager 1 approached and eventually crossed the heliopause, it delivered empirical measurements that revolutionized the field. One of the most unexpected discoveries was the behavior of the magnetic field at the boundary. Scientists had expected a sharp shift in the direction of the magnetic field lines as Voyager 1 transitioned from the Sun's influence to the interstellar medium. However, what they observed was a subtle and unexpected continuity. The magnetic field beyond the heliopods remained aligned in a way that puzzled researchers. This anomaly suggested that the heliosphere might not be as sharply defined or as neatly contained as once imagined. Instead, it could be intertwined or blended with interstellar forces in ways that challenge our understanding of the boundary between solar and galactic domains. These deviations hinted at previously unknown interactions between the solar wind and the interstellar magnetic field, painting a far more dynamic and fluid picture of the Sun's outermost frontier. In addition to its findings on magnetic fields, Voyager 1 also measured plasma density in interstellar space. Unlike within the solar system, where plasma is sparse and influenced by solar activity, the interstellar medium was found to be denser, yet cooler and more stable. This provided critical data that helped astronomers refine their understanding of the material that fills the vast regions between star systems. Voyager 1's traversal into and beyond the heliopause did more than just expand the scientific boundaries of astrophysics. It redefined the scale of our solar system. What was once thought to end at the orbit of Pluto, or perhaps Neptune, was now clearly shown to extend tens of billions of kilometers farther. Enveloped in a vast and shifting magnetic bubble, these findings are not merely academic. They have profound implications for future missions and our long-term aspirations for space travel. Understanding the heliosphere structure is essential for developing technologies that could one day protect human explorers from cosmic radiation as we venture further from Earth. It also helps in mapping the interstellar environment that any spacecraft, robotic or crewed, would encounter as it journeys to the stars. In essence, Voyager 1's study of the heliosphere turned a once theoretical concept into a tangible and measurable structure, revealing it as a living, breathing force field that protects and defines the domain of our Sun. And while many questions remain about its shape, its interaction with the galaxy, and how it evolves over time, Voyager 1 laid the first real footprints on this invisible frontier. It's a testament to human curiosity and engineering that a spacecraft launched in 1977 continues to inform us decades later about regions of space we had never directly touched before. The mission of Voyager 1 not only broadened our understanding of the heliosphere, but also reminded us that exploration, no matter how distant or difficult, brings us closer to the truth of our place in the cosmos. These contrasting environments encountered by Voyager 1 and Voyager 2 as they crossed the heliopause added profound depth to our understanding of interstellar space. Although both spacecraft pierced the boundary that separates the Sun's protective bubble from the galaxy beyond, the variations in local space weather, magnetic field intensity, and particle density between their paths suggested that interstellar space is not uniform. It is a complex and evolving landscape, shaped by both local and galactic forces. Voyager 2's instruments, still fully operational at the time of its heliopause crossing, recorded direct plasma measurements, something Voyager 1 could not do initially due to a malfunction in its plasma instrument. This allowed Voyager 2 to directly confirm the dramatic rise in plasma density beyond the heliopause, complementing the data Voyager 1 had previously inferred using its cosmic ray and magnetic sensors. This corroboration between two different observational methods provided compelling evidence for a denser interstellar medium just outside our solar system. Moreover, the turbulence Voyager 2 encountered, manifested as fluctuating magnetic fields and wave-like plasma interactions, indicated a more chaotic boundary layer. Scientists hypothesize that this may be due to differences in solar wind pressure or local interstellar cloud structures that distort the heliosphere's edge. In contrast, Voyager 1's path appeared to be through a calmer, more sensitive this frontier is to cosmic condition. Together, these findings from both spacecraft are enabling scientists to create the first three-dimensional models of the heliosphere's outer boundary, which help illustrate its shape, behavior, and interaction with the galaxy. These models are crucial not only for understanding our own solar environment, but also for contextualizing the protective magnetic bubbles that might surround other stars, possibly shielding exoplanets from harmful radiation and influencing their potential to host life. In essence, Voyager 1 and Voyager 2, though launched within weeks of each other, have become dual ambassadors to the galaxy, each offering a distinctive lens on the final frontier of our solar system. Their separate experiences highlight that the edge of our solar system is not a fixed wall, but a living, breathing boundary, shaped by the solar wind's strength, the interstellar medium's density, and galactic magnetic fields that we are only beginning to understand. As Voyager 2 continues its journey through this turbulent interstellar zone, it adds more layers to the grand narrative begun by its twin. Together, they are charting a realm never before visited by humankind. And in doing so, they remind us that even at the edges of our influence, human curiosity and ingenuity still thrive. Reaching out into the unknown, guided by the faint whispers of data traveling billions of kilometers back to Earth, journey marks both a triumph of engineering and a poignant reminder of the finite nature of even our most enduring creations. Now well over 46 years since its launch, Voyager 1 continues to drift deeper into the uncharted sea of interstellar space, carrying with it the legacy of Earth's first true attempt to reach beyond the confines of the Sun's domain. Yet, as the spacecraft travels ever farther, it faces increasing challenges. Its power supply, generated by radioisotope thermoelectric generators, RTGs, is gradually weakening. As of now, NASA engineers have been shutting down non-essential systems to conserve energy and extend the mission's lifespan. Sometime in the late 2020s or early 2030s, Voyager 1 will likely go silent, as its power becomes insufficient to sustain even the low-energy communications that still reach Earth today. Despite this inevitable silence, the spacecraft will not stop traveling. Long after it can no longer send signals or power its instruments, Voyager 1 will continue coasting through the Milky Way galaxy, a silent sentinel bearing the golden record, waiting for a distant intelligence, if such an intelligence exists, to encounter it. This golden record, painstakingly curated by a team led by Carl Sagan, includes readings in 55 languages, music from a wide range of cultures and eras, from Bach and Beethoven to traditional songs from Japan, Senegal, and Peru. Images depicting life on Earth, human anatomy, architecture, DNA structures, and the planet's ecosystems. Sounds of Earth, including the laughter of a child, the roar of the ocean, thunder, and the chirping of birds. These records serve as a kind of cosmic message in a bottle, not with the hope of rescue, but as a declaration: we were here. We reached for the stars. We tried to understand the universe and ourselves. In this way, Voyager 1 and Voyager 2 have transcended their original scientific missions. They have become monuments of human creativity and persistence, testaments to a civilization that dared to send its voice into the dark with no guarantee of reply. They represent an act of faith in the future, a belief that knowledge, wonder, and the desire to explore are enduring parts of what it means to be human. As we gaze toward the heavens, tracking the faint signals from these emissaries, we are reminded that our reach has already extended beyond the solar system, and that even in the cold emptiness of space, our story continues. The Voyager mission teaches us that the journey itself, filled with discovery, wonder, and enduring hope, is as important as the destination. Voyager 1's incredible journey has reignited the world's fascination with this fearless spacecraft after more than 4 decades of exploration. Voyager 1 has traveled far beyond our solar system, venturing deep into interstellar space. It has crossed the heliopause, the boundary where the sun's influence fades, and now drifts through a vast, uncharted region of the galaxy. In August 2022, Voyager 1 sent a mysterious message back to Earth, one that captured the imagination of scientists and space fans everywhere. Amid streams of data and telemetry, researchers detected a strange anomaly, an object of unknown origin and makeup. Tentatively named the Cosmic Enigma, this object is unlike anything ever encountered in the history of space exploration. What makes the Cosmic Enigma so puzzling? It emits faint, irregular signals that don't match any known natural celestial phenomena. Even more intriguing, its path through space seems deliberate, as if it's following a specific course through the cosmos. This discovery raises deep and fascinating questions. Where did this object come from? Who or what created it? And what might its intentions be? Scientists and astronomers around the world have been meticulously analyzing the data sent by Voyager 1, determined to unlock the secrets of the mysterious cosmic enigma. Could this baffling object be a remnant of an advanced extraterrestrial civilization, or perhaps a probe launched from a distant corner of the galaxy? Alternatively, might it be an entirely new and unknown cosmic phenomenon? The discovery has ignited a wave of speculation and debate, bringing together experts from diverse fields who are collaborating to unravel the enigma's true nature. One leading theory suggests that the cosmic enigma could be an ancient relic from a long-lost civilization, a probe dispatched eons ago, its original mission veiled in the mists of time. Whether its purpose was scientific, exploratory, or something beyond our imagination remains an intriguing mystery. On the other hand, some scientists propose that this object might be a natural celestial phenomenon, with properties that challenge our current understanding of astrophysics. This possibility reminds us of the universe's immense complexity and the vast diversity of cosmic phenomena still waiting to be discovered. It highlights how much we have yet to learn and how little of the universe's secrets we have uncovered. The detection of the cosmic enigma underscores the critical importance of continued space exploration. It calls for humanity to push further into the cosmos, to embrace the unknown, and to expand our cosmic reach. The universe is a vast, mysterious frontier, filled with wonders and enigmas that inspire awe and curiosity. As Voyager 1 continues its solitary voyage through interstellar space, carrying with it the mystery of the cosmic enigma, humanity stands on the brink of new discovery. This spacecraft has become Earth's ambassador to the stars, a shining symbol of our insatiable curiosity and unyielding desire to explore. Voyager 1's odyssey, spanning over 4 decades, has fundamentally reshaped our understanding of the universe. It continues to inspire generations of scientists, dreamers, and stargazers alike. As we ponder the mysteries of the cosmic enigma and the endless possibilities it represents, we are reminded that the cosmos is a vast, wondrous, and ever-evolving realm. Each new discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? With its indomitable spirit and enduring mission, Voyager 1 carries our hopes and dreams as it forges onward into the cosmic unknown. The story of Voyager 1 is a testament to the enduring human spirit of exploration, curiosity, and the relentless quest for knowledge. It transcends time and space, reminding us of our place in the universe and the boundless wonders awaiting us in the cosmic expanse. The enigma of the cosmic enigma serves as a poignant reminder that the universe is filled with mysteries yet to be unraveled. It invites us to continue our cosmic journey with wonder and humility, ever eager to explore the depths of the unknown. Voyager 1, humanity's cosmic emissary, continues to inspire us to reach for the stars and embrace the infinite possibilities that lie beyond.